So I guess we can just wait for 1 or 2 more minutes and then we start. Okay, I think it's time to start the workshop. So guys from CVPR, can you just confirm again that you can now see me, hear me, and see the presentation, see the slides?
Yes, everything is fine.
Okay, great. Thanks a lot. Okay, so welcome everyone to our annual Mobile AI workshop. This event is now happening for the first time, and I will start with just a few organizational notes. So our main workshop event, it happens on site at CVPR in room 103, and it also happens on Zoom at CVPR. And besides that, we're also streaming live the session on YouTube, so that later on you can also rewatch some of the videos and refer to some information that was presented during the workshop if you need it during the development of efficient models. As always, this is a very practical event. So here we are talking not just about some general performance aspects, not about the number of operations that our model have. We are talking about deployment of deploying models on real mobile AI accelerators. And as you can see on the slide, the recent NPUs that can be found on mobile devices, they are extremely powerful. Actually, if you have a recent smartphone, if you have like some smartphone that is 1-2 years old and the smartphone has some high-end chipset, then you have a very powerful AI accelerator in your pocket. And the power of this accelerator might be even comparable to the power of desktop GPUs like NVIDIA 5070, 5080. So this means that we clearly want to use it. And we just not only want to run our deep learning models on some common hardware like normal CPUs, but we really want to utilize the power of recent NPUs, or at least the power of recent mobile GPUs, and be able to deploy deployment models on this hardware. And to do this, we also need to know how to optimize models for edge devices, how to do proper conversion, how to do extra optimization so that our models are compatible with mobile NPUs. And of course, yeah, we need to know how exactly can we run them on AI accelerators. What steps do we need to perform to ensure that our AI model, our large language model, or any other model is running efficiently on the latest smartphone NPU. This is, as I mentioned, this is a fifth event. So we had for previous events, some of which were recorded, and you can also find these recordings on YouTube. So if you are interested in efficient computer vision models for mobile devices, you can clearly check these videos. And yeah, besides intro talks, there are also very useful presentations from vendors, and many of these presentations are still very relevant. Today, in this event, we'll give a new introductory talk to deep learning on smartphones. And considering the fact that the previous recordings were made more than 2 years ago, and during the past 2 years there were several radical changes in mobile ML ecosystem, we decided to make a new self-contained tutorial that introduces you to the basics of deployment of machine learning models on mobile devices and covers pretty much all aspects. So in this introductory talk, we'll try to answer the following questions. So the first one is what software to use. So you can find quite a number of different libraries that can allow you to run deep learning models on mobile devices, but not all of them are actually useful. And you need to be very careful when selecting the software that you'll be using for running neural networks on mobile. You also need to know what hardware do we have for running models on smartphones. So which NPUs are actually powerful enough to run the recent, let's say, transformer-based models, and in which devices you can find these NPUs. Also, you need to know how to ensure that the interaction between software and hardware works as intended, and you get the full performance of your AI accelerator on smartphone. Then, once you're able to run these models, you, of course, want to know which NPUs are the best for running the recent complex deployment models, and which NPUs are the best, which NPUs should vice versa not be used for anything complicated. So we'll talk about the performance of all smartphone NPUs that are available right now. And we'll talk about power consumption. So once you're running the model, you might also be interested in how much energy does this inference consume. Finally, we'll talk about not only about smartphones, but we'll go a little bit beyond, and we'll talk about NPUs that can be found in desktop and laptop processors. So quite a number of solutions have been proposed during the last 2 years. So we'll also cover this topic, and we'll talk about how we can potentially run our designed AI models not only on smartphones, but also on NPUs present on desktop devices. And finally, we'll finish this introductory talk with the discussion of the mobile AI competitions. We'll go through the past and current and ongoing competitions and tell you basically a few advices and tell you more about them, about what we expect to see from you in these competitions, and what are the target platforms and the restrictions. So after the introductory talks, there would be a number of other talks, invited talks and bigger presentations that will present you with efficient deployment design for mobile devices. Many of these talks are really interesting, and well, if you look at the slide, for instance, you can see that it's not a coincidence that the majority of talks are given either from vendors who are developing mobile hardware or by companies who are developing software solutions for mobile devices. So these guys are professionals, and they know quite a lot about practical aspects of AI deployment on mobile devices. So we'll have quite a number of different talks, so don't miss them. And again, there would be a lot of different and interesting solutions presented during this workshop. And also, of course, the majority of you will attend the main CVPR session. And there are also quite a number of interesting papers presented at CVPR conference. So we just briefly checked the list of accepted papers, and we provide you, for instance, a few recommendations where the guys are really trying to design something that is runnable on mobile devices and mobile NPUs. Well, unfortunately, still, the majority of papers that claim that they propose some efficient models, they are actually not evaluating the models on real hardware. So they're just talking about some cuts in terms of layer depths or in terms of some operators, but they are not doing any kind of real evaluation. And in the majority of cases, the resulting models will not actually run on mobile devices, despite all claims of their efficiency. And yeah, that's the reason why we're here. And At this particular event, we are really interested in learning more about what can be done with real mobile hardware and how to utilize NPUs that are available on recent devices. So now we proceed directly with the introductory talk. It will be like the duration of the talk will be almost 2 hours, and I really hope that I'll be able to fit all topics into these 2 hours. So let's go directly to the presentation. So if you decide to design some solution for mobile device, if you want to run some deep learning model on mobile device, whether it's like model doing some language processing or models doing some image classification or image processing, so whatever task you want, you generally need to perform these 3 steps. The first step, this is something where you are all experts, you just need to train your original model. So you're doing this with standard libraries like PyTorch or TensorFlow or whatever ISA library. And here you get your model, it gives you awesome results, and everything looks fine. The only problem is that you cannot run this model directly on smartphones, simply because none of the frameworks that allow you to run deep learning models on mobile devices support original PyTorch or TensorFlow or whatever formats. So because of this, you need to take the designed model and to convert this model to an appropriate format that is supported by the corresponding mobile ML library. And then once the model is converted, you can actually run and execute this model with the solution that you selected. And you can see here that one of the most important things here is to select the best machine learning library, because the steps that you need to perform here, they depend completely on this choice. And when selecting mobile libraries, you can actually find quite a number of different ML frameworks that claim to be very efficient on mobile devices, and there are quite a number of different solutions. If you just try to Google, and if you're not familiar with this field, most likely you'll find the following 4 libraries. It's TF-Lite, Onyx, Executorch, and CoreML. There are also quite a number of other libs, but they are not as popular as these 4 ones. So at this point, you actually need to make a very important choice. You need to select which library you will use. And it's hard to underestimate your decision here, because if the decision is made not correctly, you won't be able to run your model efficiently. And there are actually quite a number of caveats. And just out of the records, so from time to time, we are monitoring apps that are published in Google Play and that are trying to do some inference on mobile devices. So we're just checking, well, in particular, during the past months, we just looked at what apps are available for running large language models on smartphones locally. And we also looking at which solutions are used by guys, because for us, it's just, we're quite interested in what tools just normal developers are using. And it's hard to say how strange we feel, because in almost all cases, when we look at the pipelines that the guys are using, the pipeline is completely wrong. So the guys are just using usually the worst possible option that can be found. They're using incorrect libraries, they are setting incorrect parameters. And as a result, these models are at best running on CPUs on the latest devices, and they are not compatible with anything else. And we're actually kind of surprised that even the guys who spent lots of time on designing public applications that will do some recent tasks like run stable diffusion models or large language models, they do not really know what to use. So therefore, this step is extremely important. And if you perform a correct choice here, then the chances that your solution would be performant would increase greatly. So let's just go briefly through these 4 options. So the first option, one of the most straightforward ones, is to use Onyx. Onyx is actually a very great library and very popular library.
And one of its biggest benefits is that it allows to convert models from PyTorch to Onyx quite easily. There is actually built-in Torch tools that just allow you to export your normal model just in one line of code. So it's super easy to generate Onyx models. You don't need to do any complicated steps. So everything is very straightforward here. And yeah, Onyx has actually quite a lot of different benefits. But unfortunately, all these benefits, they are not related to mobile devices. Because on mobile devices, there is one huge limitation of Onyx. It provides you only CPU-based inference. So you can, if you converted an Onyx model and you decided to use Onyx as your runtime on mobile device, you cannot run this model on anything else apart from CPU. You cannot run this model even on GPU. You cannot run this model on NPUs, on recent powerful NPUs that are suitable, that were designed for running quite complex models and to accelerate complex networks. So you don't have these options. So, and because of this, if you're interested in something beyond CPU inference, Onyx is not your option. And you shouldn't just spend time on this because you won't be able to run the models on NPUs. So this makes actually the choice much easier now because Onyx is crossed out. Now let's move to another option. We have recently presented ExecuteTorch, and if you are designing models with PyTorch, then probably that might be actually the first option that you might consider. That okay, since ExecuteTorch is also developed by Torch, it's basically a part of Torch framework. It's quite intuitive just to use built-in tools and run models with ExecuteTorch. And if we just check the website, we'll see immediately that ExecuteTorch, unlike Onyx, it offers you to accelerate models on CPUs, NPUs, and DSPs. So everything is actually quite good here. And yeah, if we just check a little bit more the documentation, we can find that it provides CNN backend for efficient CPU-based inference. It provides Vulkan backend for GPU-based inference, and Qualcomm and MediaTek backends for inference on their NPUs. So everything is actually looking very good here because with ExecuteTorch you can basically finally run your models not only on CPU but on AI accelerators and on GPU. And now if you look at how the overall pipeline looks with ExecuteTorch, you can just find this slide, find this shim, and it shows that once you have your original PyTorch model, you first need to export this model to an appropriate format, and then compile this model to ExecuteTorch program for the target hardware, and then run this model on this hardware. And from one point of view, this looks very reasonable. So all this pipeline, it makes a lot of sense. And especially like compilation for the target hardware, you can just make the model more efficient by doing some extra optimizations and doing these optimizations offline ahead of time. But you probably can already understand that you cannot compile your target hardware just in an easy way. So for doing this, you actually need to use vendor SDK. So you cannot do this with just built-in ExecuteTorch tools. You actually need to download and install vendor SDK to compile this model to the target platform. And this significantly complicates everything. And just to give you an overview, so just to save your time a little bit, so if you decide to deploy your PyTorch model with ExecuteTorch and to run this model on Qualcomm NPUs and to use QNN, then you need to perform the following steps. First, you need to download and install Qualcomm SDK that is developed for the NPUs. Then you need to install Android NDK. Then you actually need to compile ExecuteTorch with Qualcomm's SDK. So you cannot just use ExecuteTorch models that you installed from pip. You actually need to get source codes and compile this library to be compatible with Qualcomm AI Engine. Once you compile the library, you now need to compile the model, also with Qualcomm AI Engine. And basically, the model that you're getting, it will run only with
the compiled library, and it will run only on the target platform that was used for compilation. So these rules, they apply for almost all providers, for all delegates. So you basically need to download and install vendor's proprietary library. Then you need to compile execute torch with this library. Then you need to compile the model, and then you can run the model with the compiled execute torch only on this particular library. And the only exception is CoreML, where the SDK is integrated in execute torch. In all other cases, you just need to go to vendor website, download all the SDKs, install them, set up everything, then spend quite a lot of time on compilation, on execution, and at the end you'll get a model that can be executed on NPU, but only on pretty much one specific NPU, or like one family of NPUs. And this also means that you cannot run the same model compiled with execute torch across different hardware, because basically this model is compatible only with hardware that you used, which SDK you used during the compilation. And this means that if you, for instance, want to design your application that is running LLM on different devices, you need to prepare a separate version of the application for each specific platform. So you need to go you need to use MediaTek's SDK and generate model for only MediaTek platforms, and you need to use Qualcomm SDK and generate library and model for Qualcomm platform. The same goal applies for CoreML, the same applies to GPU. Well, even GPU, if you want to use Vulkan, you cannot use pre-built libraries. You need to compile first execute torch with Vulkan, and then you will be able to run only models compiled with Vulkan only on devices supporting Vulkan. So you cannot just create a universal application and just load delegates on the fly inside it. You are limited to one specific platform in this case. And then you are getting one reasonable question. So why actually do we need execute torch if we can just use directly this vendor SDKs? And this is a very good question. So after just experimenting a bit with execute torch, we didn't find an answer for this question. So particularly for us, you're getting, well, execute torch right now, it actually creates more problems than it solves. Because a vendor SDKs, they anyway will provide you with somewhat better results. So you won't have almost any issues with model conversion, with running this model. So there won't be any extra intermediary that is causing extra problems. So, I mean, in this case, just use vendor SDK. And right now, in the current state of development, we cannot just recommend execute torch to anyone who wants to create some general purpose applications that runs AI models on NPUs. Well, I mean, unless you just want to have lots of pain in your life, because this pain will be guaranteed when you will be trying to compile execute torch with every single platform, with every single SDK, and compile the model within every single SDK, and then when trying to create like 5 different or 6 different versions of the application for each particular platform. So right now, this is not the option you might really want, especially since we have much better solution here. So you can see that now, even if we are taking the most popular libraries, our choice is already limited only to 2 options, to using CoreML and TF-Lite. And here, finally, some good news. On iOS devices, you can and you should be using CoreML. Why? Because CoreML, first of all, it offers a very straightforward way of model conversion to CoreML. You can just take whatever PyTorch and TensorFlow model and just convert them to CoreML in just same 2 lines of code. And what is more important is that you don't need any SDK. You just install these CoreML tools in Python using the provided pip package, and that's it. And the resultant, the conversion will work pretty much on any platform. You can run this conversion on Linux. You can run this on macOS. Previously, it was possible also to run it on Windows, but the recent packages are unfortunately broken, but you can still use Windows subsystem Linux to do the conversion. So conversion is very simple. And we should also acknowledge the quality of this converter. So like we try to convert tens of different models, and in pretty much all cases, the conversion was successful. And we didn't see any issues during the inference. We didn't see any accuracy issues. So like everything was working just perfectly.
something that you might not actually expect, but here this is the case. With CoreML converter, you can convert pretty much anything, including large language models and stable diffusion models. And yeah, another important aspect that CoreML, it allows you to run the models on Apple Neural Engine and on Apple GPUs. So this is pretty much the best option for accessing this dedicated hardware. It also provides you with an efficient CPU-based backend. In our test, it was performing somewhat better than all other solutions. So like all in all, if you want to deploy your deployment model on iOS devices or macOS devices, just use CoreML. There is nothing better than it. If you take any other library, it won't give you any extra benefits. And in terms of performance, the performance would actually be worse in all cases. So with Apple ecosystem, everything is clear. CoreML, simple conversion, and deployment with this tool. And when we are moving back to Android, here we have much more diverse set of devices. We have quite a large number of vendors, and we need also a solution to handle everything. And it's the good news are that we have TF Lite, and we can use TF Lite for inference on Android-based devices. And you can see here that I wrote both TF Lite and LiteRT. And for the guys who didn't check the latest changes in Android ML ecosystem, here are the news that basically Google renamed TF Lite to LiteRT. So Google removed all previous web pages that were telling you information about TensorFlow Lite. It deleted pretty much everything that was used before and now set up a new web page and made a rebranding. So it's the same library, and in the first versions there were no differences compared to TF Lite at all. So these were just the same packages but with different naming. So now don't be confused if you see LiteRT, because LiteRT is what TF Lite turned into. And the reasons for this, pretty much it's just marketing, because you know that TensorFlow itself is pretty much dead, so no one is really using it except for the guys who used it previously and the guys who need some performance solution for cloud inferencing. And because of this, TF Lite team decided to distance itself from TensorFlow itself and just pretend that it is completely independent and this library has nothing to do with TensorFlow, with Dyne TensorFlow. Instead, it's the library that allows you to run different models on Android devices, and not only Android devices. And what are the best things about LiteRT is that, everyone who used TF Lite before, you know that you can convert Keras and TensorFlow models to TF Lite and run them efficiently. But last year, Google also announced a new official converter from PyTorch that allows you to convert PyTorch models to TF Lite models just in one line of code. And this is something that we all were really waiting for, because all participants from our previous challenges, they know the pains that they had to suffer when they were trying to design models in PyTorch and then convert this model to TF Lite, because you had to use some tools developed by enthusiasts for this kind of conversion, and there were lots of issues related to model conversion. So right now you have an official tool. Moreover, this tool works quite nicely. So we have already checked it, tested it on quite a large number of models, and there are still some issues for some specific layers, but overall it works very good. And you're just getting a pure TF Lite model, which you can use with LiteRT framework. And again, these are very good news, because right now this means that you can just do all development in PyTorch, forget completely about TensorFlow, and just do conversion in a very straightforward fashion. Now, what are also the best things about LiteRT? The first thing is that it allows to run your one model across all hardware. So unlike the situation with ExecuTorch, where you really needed to convert each model for each specific platform, here you do conversion only once. So you have your original model, you take it, you run the conversion, you are getting TF Lite model. And you can run this TF Lite model on pretty much all devices.
And you can also run this model with acceleration on NPUs and on GPUs by using delegates. And these delegates do not require you to use any custom vendor SDKs. These delegates are just TF-Lite plugins that you also add to your Android application. And through these plugins, you can just access these NPUs and run all inference on NPUs. And you don't need anything else, just these plugins. So yeah, and also it should be mentioned that TF-Lite has quite good quantization tools. So if you want to get pure in 8 model or in 16 models, in 16 model, you can just use these built-in tools, and you, in the majority of cases, you'll be getting good accuracy and no significant issues with this quantization process. So now the biggest question is, okay, we are not interested, of course, in CPU-based inference. We want to run the resultant TF-Lite model on GPUs or NPUs. So I've already mentioned that we have delegates. So how to use these delegates, and actually what delegates do we have? Well, the first delegate is a standard TF-Lite GPU delegate that is also developed by TF-Lite team. And this is a very generic delegate that allows you to run pretty much any model on smartphone GPU. It supports inference on almost any mobile GPU released in the past 10 years, because it requires only the presence of OpenCL on your smartphone. And like all recent smartphones, they are shipped together with OpenCL, so no issues here. And it provides very good acceleration for the majority of deployment architectures, especially for vision-based architectures. And another very important aspect is that it can run huge models. So the particularities of GPU-based inference is that almost all GPU RAM installed in your device is available for GPU and thus available for GPU delegate. So if you have like smartphone with 16 gigabytes of RAM, then then the GPU delegate can use 16 gigabytes of RAM. And actually, you are getting a bit more lucky than the guys who, for instance, bought the recent NVIDIA 5070 GPU that has only 12 gigabytes of RAM, because on your smartphone, you can actually use more RAM for model inference. And this means that you can run pretty much everything, provided that the model is supported by TF-Lite GPU delegate. And here are also good news, because this delegate is quite generic and it supports the majority of operations and layers, unless you're using something very uncommon. The downsides of this inference, well, I mean, the first one is quite clear, is that GPU inference is generally slower if we compare this to NPU inference. But this also only refers to recent NPUs. So if you're taking NPUs released like 5 years ago or longer, all the GPUs, then most likely GPU delegate would actually show you better results than if you run the same model on the corresponding NPU. GPU inference is also, it is less power efficient than NPU model execution, so yeah, you will consume much more energy. And also GPU delegate right now, it works not the best with large language models. And the reason here is also quite standard, because large language models and in general NLP models, they contain quite a lot of logical operators. So not just convolutions, not just some operators that require to perform the actual computations. Instead, they require you to do some logical operations like tensor transformation, transposition, this kind of operators. And logical operators, they can be executed very efficiently on CPU and on NPU, but GPU is not good at this. So because of this, since LLMs, they contain lots of such operators, some models are not compatible at all with GPU delegate, because, for instance, they have 6-dimensional tensors that this is not something that's, for instance, supported by GPU delegate. Or yeah, they contain lots of operators that do not require the computation, but instead they require lots of shuffling of tensor data. So these are the downsides. But apart from this, again, GPU delegate is one of the best options if you want to develop some generic solution for vision-based problems. And yeah, this delegate would be able to run your model on pretty much ends. Then the second option, now we are moving to NPUs, and the second option is to use Qualcomm QNN delegate. And personally, we can really recommend using this delegate, because it is supporting lots of different platforms. So pretty much it's supporting everything that Qualcomm released during the past 4 or 5 years. And it delivers extremely good performance on these NPUs. So pretty much whatever recent NPU you are using from Qualcomm with QNN, you'll be able to deploy the majority of models, and you'll be able to get very good runtime results. And which is also important is that this QNN delegate, like all updates that it receives, they apply to all platforms also. So it's not only, well, if you just track new QNN releases, new features that they introducing, that Qualcomm introducing, they usually apply to all hardware, to all NPUs, regardless whether this NPU was released this year or 4 years ago or 5 years ago. And because of this, it's quite easy to develop and deploy models with QNN because you're getting pretty much the same if on one platform you don't have any issues with model acceleration, then on other platforms usually you also don't have them. So the issues are pretty much the same across all platforms. And if you are able to design, if you are able to run your model with QNN on one particular NPU, this means that most likely you will also be able to run this model without any additional issues on all other NPUs that QNN supports. QNN also provides you GPU backend to run models on Adreno GPUs. Sometimes it works better than the previously mentioned lighter tier GPU delegate, sometimes worse, but yeah, all in all, the performance can be considered as quite similar. So, but yeah, you can also use it and try for your specific model. And yeah, it also offers you lots of extra options for balancing between performance and accuracy, and yeah, some other options. So this is what refers to the latest Qualcomm NPUs. There are also previous generation Hexagon DSPs that were used for inference, and unfortunately QNN delegate is not really supporting them. So for this you need to use Hexagon TF-Lite delegate, and yeah, this from one side this delegate is already deprecated, so it's not publicly released, and you can actually find one version one binary that you might need in this Maven repository, and you can still use it for model deployment on this old Qualcomm SoCs. And like SoCs are really old, so for instance with this delegate you can potentially run models even on Snapdragon 820 that was released like 9 years ago. It still supports it, but yeah, don't expect too much from in terms of the performance and support for different layers and models. It won't be very good because both the hardware is outdated and the Hexagon delegate is also it's quite old. So yeah, if you want to run something small, like some classification models or some very simple image processing models that are dealing with low resolution, this is an option. In all other cases, probably it's better to stick with GPU delegate. So this was with Qualcomm hardware, and now with MediaTek hardware. With MediaTek, you can use Neuron delegate, and this delegate supports NPUs present in all recent Dimensity chipsets. So it provides also quite good model acceleration on all these NPUs. You can run, when it comes to the very latest NPUs, you can run even stable diffusion and large language models on them. So the delegate is actually the best choice for model deployment on Dimensity chipsets. And yeah, it allows you to run the models only on NPU and no other options. And on all other devices that are not supported, on all other platforms that are not supported by MediaTek Neuron delegate, you should use yeah, this is the only option. Other delegates that you might find is ARM delegate. And this delegate was developed by ARM and provides GPU-based acceleration on Mali GPUs that are also developed by ARM. So in our experiments, we found that it supports Mali GC71 from Bifrost family and newer GPUs. Yeah. And yeah, it also provides you with an additional CPU-based backend, also developed by ARM to run efficiently models on Cortex-A cores. Well, we actually, when we initially found this delegate, we are very curious and we just tried to test it on all platforms and compare with all other solutions. And after like trying it on almost all devices that we have,
we actually did not find too many benefits compared to TF5 GPU delegate. So the performance, if we just compare, if we average the runtime results across all platforms, then Mali, then yeah, RMNN delegate, it would be performing slightly worse than TF5 GPU delegate. So from our side, yeah, there is not much sense in using this delegate right now, because like despite the fact that TF-Lite GPU delegate is quite generic, it also has separate backends for each specific vendor. So it has separate acceleration backend for Qualcomm's Adreno GPUs, separate acceleration engine for Mali GPUs, and yeah, this engine is very good. So in case of RMNN, yeah, you can in general try to use this delegate for inference on Mali GPUs, but in the majority of cases, the results would not be much better than with TF-Lite GPU delegate. So you should know about this delegate, and maybe you should try to use this delegate, but don't expect to have to get very, very good performance and very large benefits compared to the standard execution options. And then you also have official LiteLT CoreML delegate for inference on Apple hardware. And yeah, so the only thing that we can tell you about CoreML delegate is that probably you shouldn't be using it, because the biggest problem is that it was developed quite a long time ago, and it didn't receive any major updates during the past years. So with this delegate, you can just run a few models, just a few models, and that's it. And these are very, very simple models. And yeah, one moment. Okay, so these are very simple models, so like classification models, like inception model, mobile net models. But if you are trying to run anything more complicated than that, the model will just not be delegated to CoreML at all, because it has very, very poor support for different operators and layers. So like, and as we've mentioned, if you want to run model on CoreML on Apple hardware, just use CoreML tools, take your model, convert it, and use the model with CoreML. In all cases, you will get like several times speed up for your inference. So just don't bother spending time on CoreML delegate unless you really want to have the same TF-Lite model across all platforms. Yeah, and the last thing that should be mentioned here is Android Neural Networks API. And yeah, this was actually the beginning of AI inference on Android devices. So basically all AI development for smartphones, it basically started with Android Neural Networks API. So it was introduced in Android 8.1. And the idea was quite beautiful, that instead of, for instance, using delegates, you have your NPU drivers integrated directly into Android firmware. And of course, these drivers have to be developed by NPU vendor. And then your mobile machine learning library just uses neural networks API to run the model on the target NPU. And this means that you actually don't need to use any plugins, any delegates, anything. You just have your standard model, and you just check the options that run this model with an API, and then the model would be accelerated directly with NPU. So the news are that Android and an API is deprecated. After 7 years, like it was present between Android 8.1 and Android 15, it will no longer be available. So Google officially announced this, and an API won't be present in new Android releases. And yeah, so I mean, these are actually quite bad news, because it's always good to have an extra acceleration pathway just for specific cases, because in some cases, like some vendors never developed delegates for their hardware, or do not support this hardware in your SDK releases. So with an API, you can still access, you can still run models on NPUs. And the reason, well, you might expect that, okay, this was very good tool, and like the deprecation of this tool happened because, well, of some misunderstanding. Well, as a matter of fact, no, because talking honestly, like almost everyone hated an API. And they were very, very good reasons, because it was very difficult to design an API driver. So everything was so complicated that, for instance, new vendors, they were just not able, almost unable to design an API drivers from scratch for new hardware. There were lots of issues, technical issues. Also, there were not just technical issues, but there were some personal issues with an API development and with the team that developed an API. So, like, yeah, it was the experiment. If you just ask the guys who used to design an API drivers, if you ask some vendors about the experience of doing this design, of communicating with an API team, of the decisions that made by an API team, you won't be able to hear too many good words with this regard. So, like, yeah, it happened. The idea was itself very good, but pretty much everything else was screwed up. And there were several decisions that could have saved an API, but unfortunately they were not made, only, well, unfortunately, mostly for personal reasons. So, and because of this, now we have that an API is dead, and like the tools that, for instance, we used for years, and basically our project mainly started with an API. As initially, this was the very first tool to run deployment models on Android NPUs. Like, yeah, despite all the stuff, yeah, and an API is deprecated, will no longer be available, and you have to use all other tools available at the moment. And yeah, we feel a little bit sad because we have also some good memories related to the first days of an API. And it's good that it was there, because it really helped to help the ML ecosystem, Android ML ecosystem, to develop into its current state. But yeah, so right now we have pretty much finished with an overview of frameworks. So again, as I mentioned, there are also quite a number of other smaller frameworks, but don't use them if you just do not know that you need to use these particular frameworks. So everything actually becomes, well, if you want to deploy AI model on mobile device, everything actually becomes quite simple. If you want to deploy the model on iOS, you use Caramel, that's it. If you want to deploy the model on Android devices, then just use LighterT, because it allows you to deploy just one model across all devices, and it allows you to accelerate these models on GPUs and on NPUs with the aid of the standard delegates. So this is our advice, and right now we can move to the second part of the presentation, to AI hardware. So like we already learned what software we can use, now we want to learn what is the hardware that can be used for inference. And we'll now go through an overview of pretty much all NPUs, all chipsets that provide you AI acceleration. And we start with Qualcomm-based chipsets. So with Qualcomm-based, you have all recent devices, all recent chipsets. They contain hexagon tensor processor. You can see abbreviation HTP. So all these devices, they are supported by QNN and by LighterT QNN delegate. So these are pretty much all mid-range and high-end chipsets released after year 2021. So you can access all of them with this, with either pure QNN or with QNN LighterT delegate. What models do these NPUs support? There are two types of HTPs. One type of HTPs that are found in high-end Snapdragon chipsets, and in the first generation of Snapdragon 7 line, they support quantized inference, floating point inference, and int16 inference. So pretty much you can run any model. You can just use the original floating point model, you can just do quantization and run int8 model, or you can also optionally use something in between and run int16 quantized model on them. And these NPUs are actually quite powerful. All other NPUs, they are providing only support for quantized models. So this means that you cannot run floating point models. For floating point models, you need to use GPUs. And yeah, here we also provide a benchmark scores. It's provided just for the reference, so that you have some idea to which performance category each NPU adheres. And for instance, you can see that for like Snapdragon 8 Elite would probably like 10 times faster than NPU that can be found in Snapdragon 7 generation chipsets. Like, yeah, just for the reference, so that you understand what type of performance you have.
These are recent Qualcomm SoCs. All the Qualcomm chipsets, as we mentioned, they have hexagon DSPs. So instead of hexagon HTP, you have hexagon DSP. And these are pretty much all chipsets released between year 2016 and 2020. So for them, QNN Delegate is generally not available. So QNN Delegate technically has DSP backend, but this DSP backend requires some security updates of smartphones that have these chipsets, and if this update was not made, then you cannot run any models with QNN DSP backend. And the only option that you have is to use Hexagon Delegate or an API. Well, as I mentioned, Hexagon Delegate, you can still find it and you can still use it. And in this case, you can run models on all the Snapdragon chipsets. As for the performance, again, don't expect to have something really brilliant because, well, if we just compare even the weakest NPU that can be found in recent Snapdragon chipsets with the best NPU hexagon DSP that is present on the best older generation chipsets, and you can actually even hear 2 times performance difference. And these NPUs NPUs or DSPs, so they are, what you should also know is that they are not suitable for the recent neural generation tasks. They are not suitable for running some to process high resolution images. They are really suitable for like standard image classification tasks, like all common classification models here. You can run them without problems. You can also run like simple super resolution models or like models that are not too large and that are not working with high resolution image data. So this is something that you can do this, and you can actually get pretty good results in the majority of cases. If you are moving to the recent, let's say, transformer-based architectures, or again, large language model stable diffusion, this is not for the chipsets, and the chipsets are solely for classical computer vision, for classical classification and image transformation models. And also there are a couple of extra chipsets for which Hexagon Delegate is not available. So like officially maybe it's available, but during the past years, we haven't seen a single device that can execute Hexagon Delegate on them. And these are these chipsets, and in this case, you can use only an API. And this is pretty much the entire overview of what we have in case of Qualcomm. So again, we have HTTP-based processors that can run, well, some of them can run both floating point and quantized models. Some can run only quantized models. We have hexagon DSPs that can run only quantized models, and in which case we can use only hexagon delegate, and also a couple of extra processors, extra hexagon DSPs, which can be accessed only through an API. So this is what we have in the case of Qualcomm. For MediaTek, we have a number of chipsets that are supported by Neuron Delegate, and all of them are listed on this slide. So these are recent NPUs that found in the latest Dimensity chipset. So basically, Dimensity chipset released during the past 3 years. And also we have 2 different types of NPUs here. Some NPUs, well, actually the majority of NPUs, they support both floating point quantized inference and even in 16 inference. And there are also some older NPUs that can run on the quantized and floating point models, so no in 16 support. And yeah, older models, you can just see the difference in performance between them and even, more recent and more powerful NPUs. And all these NPUs you can access through Neuron Light-RT Delegate, or through Neuron SDK. And also an API is also available for those devices, but you will get much better results if you are using Neuron. And you have the second type of NPUs that can be accessed only through an API. These are basically like the first generation MediaTek NPUs, or you can see here that it says APU because it's AI processing unit. This is a name that was used previously by MediaTek. And yeah, the first generation APUs can run only quantized models, and you can see that the performance is not good at all. So you should not be using this APUs for anything except for very simple, very basic classification models. All other models, they will simply not run on these APUs. You have second generation APUs that
support both quantized and floating point models. Well, they are also outdated, so old NNAPI drivers, and also limited to only simple classification models. Then you have third generation APU, fifth and sixth generation APUs. They are more powerful. So on these models, you can run both classification models and image processing models, like image super resolution or image enhancement models. Also, you can do this only through an API. And like, yeah, in many cases, the performance will be good. Again, don't expect that you can run the recent transformer models. No, that's not possible. Simply NNAPI drivers, they were not updated for some time, and you cannot run any complex architectures, including transformers, large language models, or stable diffusion. And one extra note that I should make is that in case of some APUs, they are not officially supported by Neuron Delegate, but you can actually run Neuron Delegate on them. So basically, MediaTek do not provide you any guarantees that it would be working perfectly or it will work at all, but still you can try to use Neuron Delegate even on unsupported APUs, and in some cases you will actually find that it works and you can get even better performance than with an API. So it was trying, and this refers only third generation APUs and new. So in this case, you can also try to run Neuron on them, and if you get lucky, then the model would be executed and everything would be working fine, but no guarantees here. So this is what happens with MediaTek. So these are all NPUs that you can find in smartphones. And yeah, now we are moving to all other vendors that provide only an API support. So these vendors are Google. You all know that Google Tensor has its NPU that supports floating point and quantized models. Right now, you can access these NPUs only through an API, despite the fact that it's deprecated. So Google is developing new delegate for these NPUs, but it's not yet publicly available. Most likely it will be available later on, but there is no particular date on this. You can also find NPUs in two Unisoc chipsets, in Unisoc T760 and T820. They provide you inference for quantized models, also only through an NPI. And you can also find NPUs in old Kirin chipsets. The first generation NPUs, they provide acceleration only for floating point models, and newer ones for both floating point and quantized models. As you can see, in case of these NPUs, we haven't even provided you with a reference score because right now these NPUs are absolutely unusable. The reason is that, well, you know that basically Huawei stopped active development of NPU software years ago, like the latest NAPI update that this chipset received, it was more than 5 years ago. And because of this, these NPUs, they, on a software side, they basically cannot support pretty much anything. Here we mentioned that they support int8 models, but actually they cannot run recently converted int8 models. So for instance, if you are using TF-Lite or Light-T and you just use post-training quantization and you can get the resulting model, this model will not be supported by the NPUs simply because an API drivers are outdated. The majority of floating point architectures, they also won't run on this NPU, so pretty much you're getting the same situation as with, let's say, first or second generation MediaTek APUs. Here they are present, they were introduced long time ago, and API drivers are outdated, and you can only use them for inference of some simple classification models that were designed like years ago, something like Inception, ResNet, MobileNet, and so on. But don't expect that you can run anything else on this. So in this case, like, yeah, you can just forget about the NPUs, and in all cases, like, we can guarantee that most likely you'll get much better results if you just run these models with GPU delegate, simply because GPU delegate supports all recent models and can provide you with quite good results during CPU inference, during GPU inference. And the last section, these are chipsets that have an NPU, but you cannot use this NPU. Well, the first one is the recent Xiaomi chipset that Xiaomi announced just a few weeks ago. yes, it has an NPU, but as of now, we don't know about the existence of any single library that allows to access this NPU. So there are no delegates, there are no SDKs, so it's available, but it's available only for Xiaomi. No one else can access this NPU. And well, it's a good question whether this NPU would be whether it would be possible to access this NPU at some point, because again, from hardware perspectives, from all specifications that we saw, this NPU is not as powerful as NPUs that you can find in recent Qualcomm and MediaTek chipsets. So even on the paper, it's much weaker. And to get a proper support for recent models, you really need to spend lots of time to design proper drivers. So like Qualcomm and MediaTek, they have quite large teams that are developing these drivers for a year, introducing optimizations, introducing supports for new for new operators, for new models, for new Gen AI use cases. Xiaomi should start basically from scratch, and it's a very good question if this would be done. Then we have recent Kirin chipsets that, well, if you look at die shows, you will also see that they have an NPU, but this NPU is technically not that much different from NPUs that can be found in these chipsets. So they are outdated. They are actually very outdated. And right now, there are no NN-API drivers available for this NPUs, nor any other delegates. It might be the case that you can access the NPUs through AI, but we haven't checked that. And all in all, like, we do not recommend you probably trying to spend time on this stuff, because again, these NPUs on the hardware side, they are quite outdated. And on the software side, you shouldn't expect much better results than with these chipsets. Simply because, you know that Huawei, they got sanctions, and after the sanctions, lots of development was stalled. And honestly speaking, these chipsets, they have much bigger problems than just old generation NPUs, because the same applies to CPUs and GPUs. Their performance is extremely bad. So they're basically like almost 5 years outdated. So like NPU is probably the last problem that you have from these chipsets, and this is also the reason why Huawei is not investing lots of time on this development, because, well, if your device hangs when you are running games, then probably the user won't be that much interested in NPU use cases. So this is what we have with Kirin, and you can explore these NPUs only if you really, well, either if you are working in Huawei and you have the job to run something on NPU, and you'll have quite a lot of pain in this case. Or if you're an enthusiast and you're just interested in what can potentially be executed on NPUs. For practical use cases, nothing really important can run on them except for simple classification models. And also, like Exynos chipsets, at some point, there was a public light-RT delegate for this NPUs. Well, some time ago, Samsung decided to withdraw this delegate, to withdraw all software support from public. So you can find some binaries, some compiled libraries, but the exact software that can allow you to integrate these binaries with light-RT, or just to run some models with these NPUs, it's no longer available. So it's NPUs right now, they're available only for Samsung. They're not available for external developers, so you can simply for now forget the presence of these NPUs in all Exynos chipsets. So this was basically an overview of pretty much all mobile processors that are available on Android market. So again, we have Qualcomm-based chipsets, we have MediaTek-based chipsets, we have Google, Unisoc, Huawei, we have latest Xiaomi, and we have Exynos chipsets. So here you can see which chipsets support which format, which chipsets support which light-RT delegate or which library. And now, if you want to run the model on this particular SoC, you will actually know which option to select and which models you can actually deploy on this particular device. And once we know this, we can go to a more thrilling part, to benchmarking, because we saw so many different devices, so many different NPUs, and you should actually be quite curious
with like what is the performance, how big models can be run on them. And for measuring the performance of these NPUs, as always, we are using a benchmark. It was developed by us years ago. So the first release was more than 7 years ago already. And like since then, 7 years have already passed and over 28 public releases. So this benchmark is relying on LightRT library, and for acceleration, for model acceleration on different NPUs, it uses either LightRT delegates where they're available, or Android and N API where LightRT delegates are not available, or CoreML in case of iOS devices. And this benchmark is measuring the various types of performance. It measures the performance of quantized models running on NPU, floating point models in 16 models. It also checks an inference speed on CPUs. It checks memory performance. It checks power efficiency. It checks the accuracy that you're getting. Pretty much everything that you might want to see, you can see while testing the platform with this benchmark. And last year, we've pushed a new update. So AI benchmark was updated from version v5 to version v6. And right now it contains quite a large set of models, very diverse models. So right now we have like almost, we have actually 30 sections and almost 30 different models. And these models start with some basic traditional computer vision models like MobileNet, Inception, EfficientNet, to more recent transformer models. So the standard vision transformer model, the standard swing model, the standard mobile vid model. There are also like almost all typical use cases are covered, including segmentation, let's say Deep Lab v3+, and all segment anything models, with tracking models. We also have image processing models like MDN, SRGAN, SRGAN, UNet, ResNet, and so on. Depth estimation models, photo processing models, video super resolution model. And in AI Benchmark v6, we've also introduced the recent large language models. So v6 version contains Llama 2 model, GPT-2 model, and yeah, a bit older mobile BERT model. And also the last AI Benchmark v6 version also contains stable diffusion model. So when running the model, when running the benchmark, you'll see whether your NPU can actually run a stable diffusion network. It's just slightly optimized stable diffusion with 1.5. So yeah, overall you have pretty much a comprehensive set of different architectures, and if you just test all these models on your NPU, you can actually get a very good overview of its capabilities, whether it can run only simple classification networks, or whether it can also run more complex image processing models, or maybe it can even run transformer and large language models. So like, yeah, this benchmark right now is suitable for pretty much any NPUs, from very simple IoT-based to the latest NPUs that are found in high-end smartphones. And yeah, the test takes usually around 20 minutes, during which you can also see visualizations of the model outputs. And after the end of the test, you can see detailed results for each test. So if you just press on the score, you can see, for instance, inference, the runtime of the model on CPU, the runtime of the model on NPU, you can see the accuracy of the model, and you can see this for every single network. And if you go to accelerate settings, you can also be able to switch between different backends. And this means that, for instance, if you have Qualcomm-based chipset, you can try to run the models with Qualcomm QNN. This is the default option. Or you can try to run these models with Android and N API. Or you can try to run models on GPU with TFI GPU delegate. Or you can try to run models on GPU with QNN GPU delegate. So like all tools are available for you, and you can run every single model on every single device with every single acceleration option. And yeah, it's even more easy to do this in Pro mode, where you have just this menu, and from this menu you can just run model on CPU, floating point and quantized, run this models on NPU. So yeah, all options are available here, and you can also see the power consumption of this model during inference. So we publish all the results that we are getting on the official website. So if you go to aibenchmark.com/ranking processors, you will see the performance of all mobile chipsets of literally
every single mobile chipset that is currently present on the market. And that was released basically since year 2012. Yeah, we even published the results of old SoCs that do not have any NPUs. But still, you can see as a result the speed of the inference on their CPUs or GPUs. So here you can see lots of information. One thing that we want to highlight that it's very good that unlike the situation that happens on desktop, in desktop environment where, for instance, the last few generations of GPUs are not showing that much progress, here we have huge progress almost every year. For instance, you can see that we got almost 20 to 30% performance improvement from the previous generations, Snapdragon 8 Gen 3 and Dimensity 9300 to the latest NPUs. So like almost every year, we're getting at least 20-30 performance improvement. And sometimes this improvement is even bigger when there is a major generation change. So like the performance rises really rapidly. And right now it already comes to quite insane levels when it's already reaching the performance not of previous generation desktop GPUs, but of the recent desktop GPUs. So like this means that these NPUs, they allow you to run very complex models, including large language models and including neural generation models. This of course refers only to the latest generation NPUs. Older cannot do this, but still. For the latest generation models, the performance is for the latest generation NPUs, the performance is really good. And yeah, this this page just provides you an aggregated performance for CNN models, for transformer models, but you can get detailed results if you press on View Detailed Results button, and here you will see the results for every single chipset for every single model. And you can just look at these results and do the analysis of how fast each NPU is for each specific architecture. So for instance, like if you are taking Snapdragon 8 Elite, you can see that if we're taking Inception V3 model, then its inference on CPU is 31 milliseconds. If we take floating point model, it's 65 milliseconds. And if you are going to NPU, then it decreases from 31 milliseconds to 0.7 milliseconds. So you have like almost 50 times performance improvement. And for a floating point model, it decreases from 65 to 1.7 milliseconds. And you also get these results for every single chipset. You can also look at the results to see which NPUs are more accurate and which NPUs are less accurate. So you can see the accuracy of the inference. So like, yeah, and you find this information for every one of 30 different tests for every chipset. So if you decide to develop some models for mobile devices, maybe you'll find this kind of information useful because you can find similar architectures and you can see whether they are supported on various NPUs or not. And also you can see here like how fast actually the performance of NPU drops if we are moving from recent generation NPUs to older generation NPUs, and you can actually see that there was almost 10 times progress during the last 5 years. So like if 5 years ago the performance of NPUs, the score was like less than 1,000, right now we have almost 10,000. And this performance, it is proportional to the latency on the devices. And also I want to give you just a rule of thumb. If you want to run neural generation models or large language models, typically this means that the AI benchmark score of the chipset should be at least 2,000. If it is less than 2,000, then in the majority of cases, you won't be able to run this model on NPU. So this is a rule of thumb. We just see, we have also large language models that we've shown you among AI benchmark tests, and we see that, yeah, if the score is lower, then usually it's not an option to run. If the score is larger, then in the majority of cases, you might be able, with some extra optimizations, deploy the model on an NPU. You have the same ranking table not only for mobile chipsets, but also for smartphones. So basically, right now you can find the results for over 600 different devices. And you can, like, for every single smartphone, you can see whether it supports which acceleration option it supports, whether like QNN delegate can actually run on it. You can compare the performance across different devices. So like, all this information is also available on the benchmark website. And also we have another separate IoT ranking table where you can find the results of IoT devices. So these are not smartphone chipsets, but more chipsets that are used in smart TVs or used for various IoT devices. So for them, we have a separate ranking, and you can also see their performance in a separate tab. So, and now I will move to probably one of the most useful things for you. So besides the results that you can find on the website, so if you are developing your own solution and you want to deploy on an NPU, you actually want to figure out whether this model, the current architecture, is compatible with NPU. And as a matter of fact, you can do it in just 5 minutes without any coding. So how to do this? Well, you remember the slide. First, you need to train the model. So once you trained it, let's say you received your PyTorch architecture for whatever task, and now you want to figure out whether this PyTorch model can be executed on, let's say, NPU that is present on Qualcomm chipset or MediaTek chipset. How can you do this? Well, you can do this also by using AI benchmark. So the first thing, you need to convert this model to LightRT format, and as we've mentioned, this can be done real easy. So in the majority of cases, you just need 2 lines of code. Whether it's Keras, PyTorch, or TensorFlow model, you're just taking your original model, running export function, and you're getting the flight model. And in like 99% of cases, your model would be converted successfully without throwing any issues. Once you got this model, just connect your smartphone to your desktop and copy this model into one of the folders. And then you need to install the benchmark. You can do it from the website, or you can do it from the Google Play, run the tests, and after the end of the tests, you can press on the promote button, go to the custom tab, and in this custom tab, you select the generated flight model, so the model that you just received 1 minute ago after running the conversion. And after this, you can select the desired acceleration option. So depending on what device you have, you can run this model with TFLite GPU delegate, or you can run this model on QNN, on Hexagon HTTP using QNN, or you can run this model on Hexagon GPU also with QNN, or you can run this model with an NAPI, or if you have MediaTek-based device, you can run this model with MediaTek Neuron Delegate, or you can use also ARM-NN, or you can use Android and NAPI. So basically all options that we've mentioned before, they are available for you. Just select the option what you want to use, and depending on this option, you will also select the hardware, so whether it's NPU, GPU, or CPU. Select some other parameters, the optional parameters, and just run. And here you are. You will see the model will be deployed on the NPU, or GPU, or CPU, and you will get its runtime results, its initialization time, so and also even memory consumption. So in this case, you can basically figure out whether the model can run on NPU or cannot run on NPU. If there is an error, it will also be thrown here. And from this error, usually you can understand that some of the layer, you can actually understand which layer is not supported, and then you can do optimizations. You can just modify the architecture and do this till the moment when everything is supported and you're getting awesome runtime here. And again, it's very straightforward. You don't need to do any Android coding. You don't need to do any complex steps. In the simplest case, you can even spend less than 5 minutes for all this stuff. And this is very helpful, especially if you are working on efficient model design and you want to develop a solution that is really efficient, and that is efficient not only on the paper, not only like on the numbers that you're getting in terms of the number of operators that your model has or the number of flops, no, but that the model is efficient in practice, that the model can really run on NP. And from our side, we feel that this is really satisfying when you develop something that is really practical. And once you've done this, once you've used the step, you can now actually move back to the first stage to training your model and now play with different architectures. You can just try to, well, you don't need actually even to do some major design change to retrain the model. You can just try different model designs, like initialize models randomly and convert each model design to TF-Lite and then run each model design and see how the latency of the model changes depending on one or other architectural change. And like this is a very straightforward way how you can not only just run the model, but how you can develop efficient architectures. So just you're getting continuous feedback, you are defining an updated model architecture, converting, running. If the results improved, you understand what caused the improvements, and you can do further optimizations. So quite simple, quite straightforward, and we find it very useful. So ourselves, we are using this tool for our own development. So yeah, so right now we've finished with an overview of the performance of just computational performance of the models, and we can just briefly talk about power efficiency. A benchmark, besides providing you with pure performance of NPUs, it can also provide you with power efficiency tests. It has a separate built-in power efficiency benchmark. So technically, yeah, if you just once you reach the final web page, you can just press on this plate to press on this planet, and after this, you will it will bring you to across a separate standalone test. And in this test, we run on the standard computer vision models that are supported by pretty much all NPUs to ensure that this test is measuring really NPU-based power efficiency and not a CPU-based or GPU-based. So it was important that all models should be supported by NPUs. And you can run floating point and quantum models, and you can see what would be the FPS per watt values depending on different performance mode and on different devices. And before going to an overview of the results, let me just show you some graph where you can see an evolution of power efficiency values across different generations of Snapdragon devices. So it shows you FPS per watt values for unit model, for quantized unit model, for all Qualcomm chipsets starting from Snapdragon 835 released in 2017 till the recent Snapdragon 8 Elite chipset. What I really like about these graphs, about power efficiency graphs, is that they can actually tell you much more information than just power efficiency values, if you are able to read them. What is the most important hint here? That power efficiency, it highly depends on the architecture of the NPU. And by looking at power efficiency graphs, you can actually see when the architecture of the NPU was changed radically, and how big the changes of this architecture were. So if in particular, here you can see that the first two generations, 835 and 845, they show pretty much the same FPS per watt value. And this is actually not surprising because the architecture of the hexagon VSP that used in these two chipsets, it was very simple. So 845 received some updates, but they were not revolutionary updates. Big updates were received by Snapdragon 855. So in this case, this generation was moved to V66. And yeah, so here we got a new generation of NPUs, really a new generation. And we can see that it also caused almost 2 times power efficiency improvement. And in case of Snapdragon 865, there was also some extra improvement, but it was not so big. And guess why this happened? Because 855 and 865, they had very similar hexagon DSPs. The architecture was very similar. They both are of architecture V66. This is an internal Qualcomm name. And again, you cannot find this information from some presentations, or sometimes you cannot even find this information from technical papers, but you can find this information just by observing this power efficiency graph. And then we see some very unreasonable thing. We see some very huge drop, a very huge increase. So basically, FPS per watt values increased by almost 10 times. Why this happened? Because at this particular moment, Snapdragon 888, it received a completely different NPU. So the previous NPUs, they were actually initially developed even before the AI boom. So they are heavy modifications of the NPU found in Snapdragon 820 that was released in 2016. And at that moment, it was supporting AI inference, but it wasn't, well, these were the early days of AI on mobile devices, and actually not only of mobile devices. So the really huge architectural updates were received by Snapdragon 808 when NPU was completely redesigned. And you can see this redesign here. So you can see, like, again, 10 times difference in terms of power efficiency. What is more interesting is what happened later on, because you might expect that, okay, that's an issue, that's an error on our graph, because, well, I mean, how can it be that the next generation of Qualcomm NPUs became twice less power efficient? So it cannot be, they cannot be insane, right? They should act logical, and they cannot just present new NPUs that is twice less power efficient. And there is actually a very good explanation for this, because Snapdragon 888, it was supporting only int8 inference. It contained only int8 cores, only cores that can provide integer-only inference. Starting from Snapdragon 8 Gen 1, this NPU also received floating point cores. So this means that starting from Snapdragon 8 Gen 1, you can run not only quantized models on the NPUs, but also floating point models. And yeah, this introduction also had its costs. So you can see this cost in terms of power efficiency. So the NPU became twice less power efficient due to extra floating point cores that also consumes energy, even if your model runs quantized only network. But yeah, apart from this drop, actually Snapdragon 8 Gen 1, it was more powerful, and it was extremely useful because you were able to run just original floating point models. And in cases when you cannot quantize, or when quantization causes huge accuracy drops, you can just stick with the original floating point architectures, and yeah, you will be able to efficiently execute them. But you see that just this graph, it explains you the changes that were made in NPU design. And you can also see that 8 Gen 2, 8 Gen 3, 8 Gen 8 Elite, they show almost the same power efficiency results. And this also suggests that, yeah, this new NPU, they become more efficient, they have more cores, they are more performant, but overall we are dealing with more or less the same NPU design. And all this information we can infer just by looking at this power efficiency graph. No other, we don't need any documentation, any experiments, no. We just look at FPS per watt values, and we can infer lots of technical stuff happening under the hood. And you can see the same graph if you're using other models, like SRAM models. In some cases, like architectural changes that were made, they started supporting new layers and became more efficient in execution of some mobs. So for instance, in case of D++ with 3+, you can see that new Snapdragon chipsets, they are far more power efficient than even Snapdragon 888. But yeah, the overall idea stays pretty much the same. Several generations, and these generations can be easily distinguished between each other just by looking at this power efficiency graphs. So if we are looking at power efficiency ranking, we can see that recent NPUs are extremely power efficient. So they show also quite insane FPS per watt values for the majority of architectures. And we can also see that Qualcomm and MediaTek, they are far better than other vendors right now. I should also make one disclaimer that these power efficiency values were obtained when running the models in burst mode, which means that it was using the full performance of the NPUs. Technically, you can get much better FPS per watt if you are using if you're using power efficiency modes, but the problem is that in these cases, FPS values would also drop, and they would drop significantly. So just by switching from fast single onset to sustained speed, usually the drop in FPS is 2 times. So the inference speed would increase by a factor of 2. And if you go into more power efficient modes, then usually this drop is sometimes 5-fold or even 10-fold. So to simplify the comparison between different NPUs, we decided to add the results in fast single inference mode, when basically NPUs show the highest performance here. And here you can see the results for floating point inference. These are basically the same models, but instead of running quantized models, we're running floating point models. And here you can see how much quantized models are more power efficient compared to floating point models. So for instance, for Snapdragon 8 Elite, for quantized models, we're getting 60 FPS per watt when running quantized networks. And when running the corresponding floating point models, we are getting only 12 FPS per watt on average. Oh, no, 13 FPS per watt on average. So we're getting 4 times FPS per watt decrease when switching from quantized inference to floating point inference. And therefore, if you are really interested in power efficiency, if, for instance, you have some tasks that should run continuously on a device, it's very important that you are using quantized inference, because it will consume usually 4 times less energy, and sometimes the gap can be even bigger. And yeah, overall, we can also see here that almost all recent SoCs and NPUs are very power efficient, even if we're talking about floating point models. So you're getting still quite good value. So yeah, use NPUs if you want to deploy a solution on use NPU inference if you want to deploy your AI model on mobile devices, because it will not only give you much better runtime results, but it will also cause much lower power consumption. And we are moving to the last technical topic, to going beyond smartphones. So during the previous slides, we were just talking about smartphones, smartphone NPUs, smartphone GPUs, and so on. But I mean, I expect that you all are quite technical guys, and most likely you've seen the presentations from desktop vendors, and you saw that almost all of them right now have NPUs embedded into desktop hardware, into desktop processors. For instance, during the last year, Intel introduced new Lunar Lake generation of processors that now integrates fourth generation NPU in them, and the same was done by AMD. So the new series of Ryzen processors, they also contain a dedicated NPU. So this suggests that probably we can also run our models not only on smartphones, but we can technically run these models on NPUs that are present on desktop systems, on desktop processors, on laptop processors. So, and then we should probably also take a look at what hardware do we have here. A more interesting fact. So you also saw that Snapdragon, for instance, introduced new Snapdragon X Elite chipsets for laptops. And if you look quite closely to the diagram, to the shim of this chipset, you will see our familiar hexagon NPU. That technically is the same NPU that is present in Snapdragon 8gen 2 chipset. So actually, we've already run models, AI models on them, and we've even benchmarked this NPU on Snapdragon-based mobile chipsets. But yeah, technically, you have the same NPU present in your laptop if you've bought recent laptop that features Snapdragon X Elite platform. The same also works for Apple Silicon. So if you check, for instance, latest Apple M4 chipset that is present in recent Mac Minis, it also has an Neural Engine, and you won't be surprised that it's exactly the same NPU that is present in the latest iPhones. It's NPU that is present in Apple M14 Pro, M18 Pro chipset. So we not only have NPUs in some of the desktop chipsets, we sometimes even have the same NPUs that we have on mobile device. And this also tells you that if you design a model that can run on mobile device, on mobile NPU, then it's quite likely that you will be able to deploy this model on desktop system. And right now, like previously, everything was quite simple here. We had NVIDIA GPUs and we were able to run AI models on them with CUDA, or otherwise we had to use just CPU cores. Right now, the situation became much more interesting because right now we have dedicated AI accelerators in Intel processors, in AMD processors, in Snapdragon lineup, in Apple lineup. And also you can run AI models not only on NVIDIA GPUs, you can also run on all other GPUs, either through vendor SDKs or by using, for instance, Windows DirectML. So right now you got quite a large opportunity, quite an extensive opportunities in terms of what hardware to use for inference on your desktop systems, which means that which means that it would be very interesting to see what is the actual performance of these NPUs of this hardware. Because I mean, you should be at least curious. For instance, if you have recent Intel laptops and the models that you are developing, can they actually be deployed on this NPU? And well, how good performance they will show compared to GPU inference. So ideally, we would like to use a proper benchmark to compare all platforms and to see like what platforms can really do. Not just use this marketing information by which vendor tells that they every year they get a 10 times improvement compared to previous generation NPUs and compared to competitors, but real performance, really just compare all AI silicon across different vendors under exactly the same tasks. And yeah, I mean, it would be really good if we can run a benchmark model on them because it contains pretty much everything that is needed for benchmarking of this kind of systems. Because again, there are some classical models for NPUs that are not very powerful. There are much more complicated models for more performant NPUs. And again, we have even typical LLMs and stable diffusion models that users right now want to run on their machines. So like, yeah, it's pretty much a very extensive set that can cover almost all hardware. Yeah, and the only problem is that, AI benchmark is Android based and none of these platforms really supports Android. And of course, none of the platforms offers any delegates for light-RT or like any other options to access the NPUs if you are running Android. If you like by chance installed Android on them, yeah, it won't work. And yeah, that's quite unfortunate, and this means that we cannot run a benchmark on them. Well, I mean, we cannot run if this is an Android benchmark, but we can run this benchmark if this benchmark turns into a Python-based benchmark. And we are happy to announce that we've actually ported a benchmark to Python and made a full reimplementation of all workloads of all models to ensure that all current tests they can be executed with pretty much any framework of your choice and can be executed on any hardware. So the new version of AI Benchmark V6, it contains absolutely the same tasks and the same models. But now you can run this, but now you can both use different frameworks. You should not only use Android, but you can just use Onyx, you can use PyTorch, TensorRT, TensorFlow, LightRT, Core, whatever framework you want. And this means that all models that are present in the original AI benchmark version, they were also converted to the corresponding format. So right now, AI benchmark models are also available not only as LightRT models, but also as Onyx models, as PyTorch models, as TensorRT models, as TensorFlow models, as CoreML models, and even more frameworks are coming. So what does this mean in practice? For the majority of frameworks, you have different acceleration options, and you can run models with acceleration on different hardware. And this really creates an insane number of different acceleration pathways that you can use while running the inference with the AI benchmark. So suppose that you just selected Onyx backend, and you remember that I told you that you shouldn't use Onyx on mobile devices because you can run the models only on CPUs. Yes, and that's still the case, but the situation changes significantly if you're moving from mobile devices to desktop devices, if you're moving from Android and iOS to Windows, Linux, or macOS. Because here you can run these models with CUDA on NVIDIA GPUs. Or you can run these models with DirectML on any GPU supporting DirectX 12. Or you can run these models with QNN on Snapdragon X Elite devices, or NPUs. Or you can run them also with TensorRT on NVIDIA GPUs. Or you can run them with AMD ROCm on AMD GPUs or with AMD VDs on AMD NPUs. Or you can run them with OpenVINO on Intel NPUs. Or you can run them with ARMNN on ARM hardware and ARM GPUs and NPUs. Or RKNPU on Rockchip NPUs. Or run them with CAN on Huawei devices. So you have lots of options within just one framework. And if we are taking different frameworks, we are getting much more options, even more potential acceleration backends. So you can, even like with PyTorch, you can run them with CUDA on NVIDIA GPUs, with ROCm on AMD GPUs, or with MPS on Apple Metal GPUs. And yeah, with TensorFlow, you can do the same, but here you also have TensorRT option and DirectML option. So you can actually run the models with acceleration on all platforms, on all Windows, Linux, macOS platforms, and on all chipsets, on all devices. What does this mean in practice? This also means that you can not only compare the performance of different NPUs or different GPUs or different hardware, you can also compare the performance of different frameworks within just one platform. So here is an example. You can take Mac Mini machine that was released last year with Apple M4 chipset that has this Apple Neural Engine. And you can run the models with CoreML, with just pure CoreML on Neural Engine, and you will get some results. Or you can use models with Metal on Apple's GPU, and you can see that the results actually get worse, but not that worse. Or you can use Onyx and use with Onyx CoreML execution provider also on NPU or on GPU. And you're also getting some performance, and you can see that, for instance, here the performance is twice worse compared to pure CoreML. Or you can use TensorFlow, and that was one of the most surprising facts, that for TensorFlow we have a very powerful TF Metal plugin that allows to run models, to run both training and inference on Apple GPUs. And moreover, it performs quite decently. So the performance is much better than we expected. Or you can use PyTorch and use the same plugin, but yeah, in this case, the performance is not very good. And of course, you can use other frameworks. So you can actually compare the performance of different frameworks, not only of different hardware here. You can do the same, for instance, with NVIDIA GPUs, and you can use run models with PyTorch and CUDA. Probably this is the option that you're all using when designing your models. And well, here are some good and bad news. So we know that lots of guys, when they're developing efficient models, they're usually reporting the inference speed of the model on NVIDIA GPUs when using PyTorch. So here are the news. You can actually get almost 4 times better inference times just by switching from PyTorch to Onyx and switching from CUDA to TensorRT backend. Because, well, as it turns out, PyTorch CUDA backend, it might be good for training. It might not have that huge issues when you're training the model, but it doesn't really perform well for inference. And it doesn't depend on the particular model architecture itself. It's quite poor. And even TensorFlow performs much better for inference. And this is basically the reason why some guys are still using it when they are deploying models in the cloud or when they really need efficient solution. And you can get, again, even better results when you're moving to Onyx, and it's super straightforward. As you remember, from PyTorch to Onyx, conversion can be done in one line of code, and you can run the resultant models with CUDA backend, and you'll already get quite good acceleration. So yeah, even in this simplest scenario, scenarios that you are familiar with when you're training PyTorch models and you want to run these models and you want to measure the inference, you can get 4 times difference just by switching from one framework to another. And this switch won't usually take you more than 10 minutes because it's quite straightforward. And we can be even more insane, and we can go from comparison across the same hardware type to comparison across different hardware types. So as we've mentioned, these are the same models. And also what is important that the scoring system, everything is the same across different platforms. So the scores that you saw on NVIDIA GPUs on Mac hardware, they are directly compatible with the results that you see on mobile devices. So if you get the score that you achieved on Snapdragon 8 Elite device, and if you receive the score that you received on NVIDIA 2080 Ti, the scores, you can just compare them directly because they run exactly the same models under exactly the same conditions. And yeah, this is just apple to apples comparison. And here you'll see the surprising fact that actually Snapdragon 8 Elite, it performs even slightly better than NVIDIA 2080 Ti. And well, for us, it's quite expectable because we saw this evolution of mobile NPUs during the past years. And as I mentioned, this evolution was extremely rapid. From one generation to another generation, sometimes performance improvement was by a few times. And this is not surprising that the recent NPUs, they are already reaching the performance of recent generation NVIDIA GPUs. Because, I mean, in the case of NVIDIA GPUs, there is not that much progress, unfortunately. And in some cases, we even saw some degradation. But luckily, this is not the case in case of mobile world. And therefore, the original gap that was between mobile inference and desktop GPUs, it was considerably large, but it was just decreasing from one generation of mobile NPUs to another. And right now, if you are deploying your module on Snapdragon 8 Elite NPU, you can expect to have the same performance as if you were deploying the module on NVIDIA 2080 Ti. And you can now infer all this information by using a benchmark. So it compares not only across one specific niche of devices, it compares the performance across different niches and across absolutely different types of hardware, starting from low power IoT NPUs to dedicated desktop GPUs. So just to summarize, so since now AI benchmark is also available not only for smartphones, but for pretty much any other hardware. So it supports already ONNX, PyTorch, TensorRT, TensorFlow, LightRT, and CoreML backends. Technically speaking, we can also add support for some proprietary vendor libs. The only requirement is that they should have Python API because all communication with the libraries right now happens through Python. But like it's not a problem in our world where like almost all libraries they expose Python API. And right now we are now in beta testing, so this AI benchmark version and its source code is available to official AI benchmark partners. During the summer, we'll start rolling out binaries for the end users and for all other audience. And you should expect to see much more detailed results quite soon, and you will finally see how good results you can get when you are running the models on Intel NPUs, on Qualcomm NPUs, on various GPUs, how good is DirectML compared to CUDA or NVIDIA ROG or AMD ROCm. So all this information will be coming soon to the official website. And we'll also be publishing all results, same as we've done with mobile devices, and just by visiting, you'll be able to find all the information. And hopefully we'll discuss all this data during the next meeting that will either happen this October at the ICCV conference or during the next mobile AI venue. And yeah, just one last note for if you see that some machine learning backends are currently missing, or like there are some platforms that are not yet covered by a benchmark, or you just want to learn the results that we are getting on some particular platform, just drop us an email. And yeah, this information is primarily to vendors. So especially to IoT vendors, because we cannot just from the beginning cover everything. So if you're interested in adding your backend to a benchmark, just contact us directly and we will talk about technical stuff. So we've covered almost all topics. We've discussed software that can be used for running models on mobile devices, and we now know that in case of iOS devices, we can run models with CoreML, and in case of Android-based devices, it's better to use LightRT. We know what hardware we have on all mobile devices on all mobile SoCs. We know what acceleration options are available, we know their performance, we know their power efficiency values, and we even know that we can deploy models not only on mobile devices, but we can also deploy models on desktop hardware with NPUs, and you already saw suggestions that we can do this with Onyx, for instance, with Onyx execution providers. So right now we're moving to the last part to discussing some real use cases, and we'll discuss the past and pretty much ongoing mobile AI competitions. So once you've learned all the stuff, you are welcome to start developing solutions for mobile AI challenges that we are hosting at CVPR conference and that we continue at ICCV conference. In these challenges, the rules are pretty much the same for all of them. There is one task, like super resolution or denoising or large language models development. For this task, you usually have a data set that is used for designing the models that would be used for testing your models. And you have your target platform on which the runtime of your solution would be measured. And your goal is to design the most efficient model for this particular platform. With we had these workshops, these competitions at CVPR with the current mobile AI workshop, and like the deadline was for these competitions was like almost 2 months ago. But we've restarted these competitions, and the next deadline would be with ICCV conference on the 9th of July. So you still have 1 month to design solutions. And now I wanted to go briefly through all of them and just give you a few notes about the requirements and just a few hints in case of some of the competitions. So the first competition is 4K quantized image super resolution challenge. This is pretty much the same challenge that was running with mobile AI workshop with CVPR, but right now there are a few changes. The first change is that the target resolution increased from Full HD to 4K. So right now you're super resolving images of size 720 times 1280 pixels to size 200 1060 to times 300 840 pixels. So you're really moving to 4K resolution. This is this makes the task a little bit more challenging. But we've changed the platform because previously we used Google Pixel NPU, and you all complained about it, and there were some good reasons for complaining because this NPU has very unstable drivers and you suffered quite a lot. And we've also discussed this briefly during the presentation of challenge results. So in this challenge, we changed the target platforms from Snapdragon 8 Elite or from Google Pixel to Snapdragon 8 Elite. And its NPU, as you've already seen during the presentation, as you've seen on the past slides, it's far more performant compared to Google Tensor NPU, and you've already seen that it's almost as performant as the NVIDIA 2080 Ti. And this means that, and also this NPU can even run stable diffusion models and large language models, so it's really capable. So despite the fact that the requirements increased, that it's no longer Full HD but 4K resolution, the task actually became simpler because you have very good QNN backend, and this means that almost all models would be accelerated, again, unless you are using something extremely custom. And that the performance would be even better than the performance that you had before. Note that there is also one extra constraint that the PSNR score of the model should be greater than 30 dB, and we are doing this to ensure that the quality of the resultant solutions is sufficient, that these solutions can be used in practice. Because everything that is less than 30 dB, it's usually showing not enough fidelity performance. So with this competition, everything is quite clear. Target evaluation platform is Snapdragon 8 Elite, resolution 4K, minimal PSNR score is 30 dB, and the model should be quantized, same as before. For runtime evaluation, for local runtime evaluation, if you go checking this presentation carefully, you remember that you have QNN delegate, and if you have some recent Qualcomm-based smartphone, whether you have personally or one of your colleagues or one of your family members, this means that most likely you will be able to run your model locally on this smartphone on Hexagon NPU by using AI benchmark. And you can just test and profile the model on your own smartphone. You don't even need to use any other platform. And again, if your model runs successfully on this NPU, this means that it will most likely, like 90-something% guarantee that it will be running successfully on 8 Elite platform, because QNN delegate is quite generic. So if it runs on one device, usually it also runs on all other devices, on all other NPUs. So you also have quite a straightforward way of profiling the model on your local smartphones. And here, as well as in all other challenges, we allow you to send us up to 3 models every week, and we'll run these models on Snapdragon 8 Elite and provide you with the feedback in the reply. So you can also get your results on the target platform. You can send us your models and get the runtime results. And if the models do not run, we can tell you what. Sometimes we can tell you what is the issue. Well, at least, yeah, if the issue is related to supported layers, we can just also give you an information on what layers failed. So this is what refers to 4K quantized image super resolution. We have also another challenge, a new one that is 4K super resolution, but it's not quantized, but it is floating point. The guys who participated in the quantized image super resolution challenge, please pay attention that there is an extra competition. This competition is pretty much the same. The only major difference is that you do not need to run any quantization, any module quantization, and this also allows you to design everything in PyTorch, because you don't need to use any post-training or quantized aware tools. Just design your PyTorch model, train it, and convert directly to TF-Lite. In this case, as a target evaluation platform, we're using MediaTek Dimensity 9400, and as you've seen, this is also an extremely powerful platform, showing almost the same performance as Snapdragon 8 Elite. So its NPU is also very, very powerful. In this competition, the constraint was accuracy constraint was increased further. It's not 30 dB but 31 dB, but at the same time, you don't need to quantize the model, which gives you an extra score in terms of model accuracy. And it's not very difficult to get to 31 dB of PSNR. It's a bit harder to push it like further to 34, 35 dB, but 31 dB is not a problem. So here you can really focus on the architectural changes, on which architectures are efficient and which not efficient, and And same as in quantized image super resolution, you can send us your models 3 times a week, and we'll give you a feedback as for the runtime on the target MediaTek Dimensity platform. Then we have real-time video super resolution platform. The constraints are the same as before. Again, here we also introduced baseline constraints that PSNR score should be greater than 28 dB. The runtime evaluation now is on Adreno and Dimensity GPUs. And Mali GPUs. So this simplifies everything a lot. This means that you can just profile your model locally, because it doesn't matter what smartphone you have. If it's an Android-based, you can use TF-Lite GPU delegate and try to run this model and test this model with this GPU delegate. And usually the runtime on different platform is proportional to each other. So for instance, if one GPU is twice faster than another GPU, then the runtime on this GPU would be twice lower compared to the second one. So this means that you can actually do all optimizations on your own device. And we also, in these challenges, we also provide you with an opportunity to send us your models for testing on the target platforms, but there is actually not much need here, because you can just do all development, real-time and real-time testing on your own hardware, and the results would be as relevant as the results that you are getting on the target platforms, because this delegate is very generic. Then we have image denoising challenge with fixed links to the datasets. Again, don't check the minimum PLCNR constraint. Again, all constraints here, it's not difficult to beat them, but they just establish the basic levels above which the basic levels in terms of model quality, because everything that is lower than this threshold usually provides a quality that is not satisfactory. And the results that you're getting, they are not very practical. So yes, you can get like 35 dB per SNR and your model would be doing some sort of denoising, but you won't be willing to use this model yourself because it will introduce lots of artifacts. And usually everything less than 37 dB, its performance is not okay. So yeah, this is with image denoising challenge, bokeh effect rendering challenge, again, mobile GPUs as target aggregation platform. So everything is very clear in terms of testing your device locally. One extra note here is that in the majority of competitions, you can see that we've also imposed one extra constraint that your results should make sense, your visual results should make sense. Because in all competitions, we are checking visual results that your models are producing. And if your model produces lots of artifacts, then your model would not be able to win. We're not talking about some very low-level artifacts, so we won't be looking at pixel assembly or something like this. The majority of models, for instance, we checked the results that you sent us in the previous bokeh effect rendering challenge, and there were quite a number of solutions that were just blurring the entire image. Yes, the PSNR numbers were quite okay, but the results were not making sense. You cannot even use this model for anything because you're just getting a blurry image, and this blurriness is almost random. So even if you're getting very good PSNR scores, don't forget that the results should make sense because all these competitions, they are quite practical ones. So we want to get the solutions that can be used in some real cases. And yourself, you should also be willing to design something that makes sense. That, for instance, yourself, you would be willing to use, or you would be willing to show this to whatever your colleagues or to your friends or so on. And not just trying to overfit to PSNR number and that's it. So please keep this in mind that all solutions would be also tested in terms of visual results. And if the solution introduces lots of artifacts, or if the results would not make sense, then the solution would not be would not be able to become a winner, even if PSNR scores are the best ones. But again, we're talking not about some very small minor issues. We're talking about constraints like corruptions, blurriness, inappropriate colors and so on. Then we have sRGB image enhancement challenge. Again, same platform. The model would be tested on mobile GPUs. We have baseline PSNR thresholds. The resolution is Full HD here. And learn smartphone ISP challenge. In this case, note that the resolution was increased from Full HD to 5 megapixels to stay closer to the current real use cases. It's the same data set. There is also some basic PSNR threshold and the same target evaluation curve. And we have also two other challenges, experimental ones. One challenge is efficient stable diffusion model. These are so-called open challenges. So we do not provide any particular dataset. So you can use whatever dataset of your choice. And we allow model submission in different formats. So for model evaluation for the models that you're sending us, we allow you to use CoreML, Onyx, PyTorch, and TensorFlow. The model runtime would be tested on Apple M4 platform here. And it's pretty much up to you to decide which pathway should be used. So of course, you can just design the original model in PyTorch and send us PyTorch model, and we'll run it on CPU with Metal backend. But yeah, again, don't expect that the results will be very good. And in this particular challenge, the emphasis is mainly on the runtime of the models, on deployment of the models on some particular device. So in this particular case, it would be good if your model can actually run at least on GPU. And therefore, we strongly recommend you to use at least Onyx and use either Onyx CoreML Metal backend, or ideally, of course, Onyx, Caramel, Apple Neural Engine backend. So in the best possible scenario, you can optimize the model so that it runs on Apple Neural Engine and you'll get the best possible runtime. Again, the optimizations that you'll be doing, they are up to you. You can do structural optimizations. You can just play with different layers. You can remove some features from the model. So everything is completely open. You even do not need to train anything from scratch. You can take the existing model and just try to optimize it for this specific platform. We will be testing the setup as you've provided. So there is no intermediary test phase. There is only final submission in this challenge. So this means that you are sending us the entire pipeline. You are sending us Python code that allows us to introduce some input prompt, and the model should generate the output. And we'll be measuring the speed of this generation on this target platform. As for quality, we'll be measuring it using mean opinion scores. So we'll be using 50 different input prompts, and for each input prompt, we'll look at the results that your model generates, and we'll assess it using mean opinion scores using the user study. So this, in this case, your models will be evaluated really in using practical use cases. So this means that the target of the model is to generate some image that the end users would be happy with, and this would be the same accuracy evaluation. So your images would be shown to the target users, and they will grade each image whether it corresponds to the input or not, to input prompt or not, whether it has a good, it is of good artistic value or not, and so on. So again, on the final submission, all models would be checked on the same Apple M4 platform. We'll be checking, we accept for different frameworks for model implementation, and the solution that shows the best visual and numerical results wins. Very simple. And the same also applies to large language models challenge. Here, the setup is a little bit easier because here we will be using Raspberry Pi 4 platform. So this means that only CPU-based inference, and you're allowed to use also Onyx, TF-Lite, PyTorch, and TensorFlow frameworks. And as you can already, from the previous presentation, you can already know that it would be much better if you're using Onyx or TF-Lite frameworks, because in this case, they will give you the best inference speed. And again, the quality of the models would be assessed in the user study using mean opinion scores, and the runtime, it will be just CPU-based runtime, because we know that LLM's optimizations for NPUs is much more complicated. Therefore, we just used the simplest scenario. Maybe in the next competition, we'll be using NPUs, but right now everything is very simple, so that you can just, again, take whatever model, do quantization, do pruning, do whatever optimizations you want. And we'll just take your model, run it, evaluate the results in the user study, and evaluate the runtime on the Raspberry Pi platform, and the fastest and the most accurate solution is. So the deadline is July 9th, as we mentioned, so you have still 1 month until the end of the challenge and submission of the papers. Initially, we wanted to make the deadline much later, but unfortunately, ICCV changed a little bit the rules, and right now they require all paper metadata to be submitted before the 11th of July, which means that we have to stop everything and finish paper submission also before the 11th of July. So if there are some changes, we'll notify you later, but right now we are not planning to do any shifts here. So you have still 1 month. This is quite a lot of time, and you know pretty much all rules. You know the competitions, again, 9 competitions, different tasks, different target platforms for all competitions except for large language model and stable diffusion. You can send us the models for runtime evaluation, and the best team wins. And don't forget that you can also submit a paper to the workshop, and the paper is describing your solution. So if your solution makes sense, then the paper would most likely be accepted. So that's it. I'm already 10 minutes late. Just a few final notes. You can also find some useful information as for model design in the previous mobile AI challenge papers that describe the solutions. So there are still lots of useful ideas there, and I hope that especially if you just want to participate in new challenges or if you want to design a solution for one of the tasks, I strongly recommend you check in challenge papers because they already provide you with a good overview of different solutions, different approaches that the previous participants tried and how efficient they were. And yeah, you can find challenge papers from 2021, 2022 on the workshop website. Today, right now, we'll move to presentations from vendors and from the authors of the papers that were submitted at the workshop. And again, many talks are extremely interesting and extremely relevant for you if you design to develop models for mobile devices and to do some optimization. So please don't miss them. And right now, that's the end of the talk. I think we can just have pretty much 5 minutes. 5 minutes for questions. We are like already 10 minutes late, so just in case some of you have questions that related to the current, related to the materials that I've just described, we can just have a very quick discussion right now. And for challenges, we'll have a discussion at the end of the workshop. So all of you who has questions regarding the competitions, regarding the rules, you can ask them at the end of the workshop. So yeah, I guess I stop presenting my slides. So any questions from main CVPR conference, from room C103 or from the users in Zoom, or from those who are watching us on YouTube? Okay, seems that there are no questions. This means that it's time to move to the invited talk.
I have a question.
Okay.
I assume this is fine for me to be doing it from here. Yeah, I was just curious. Thank you for the talk. Super interesting, amazing overview. Been a fan of your work for a while, actually, so it's cool to see the presentation live. I'm curious how you measure power consumption. So the denominator in the power efficiency metric that you report, right, FPS over watt.
Yes.
How do you actually measure the watt? Is it an estimation based on like utilization system metrics, or is it? Yeah, just would be curious to know more about that.
Yeah, we actually use 3 different options to do these measurements. The first one, this is what is used by AI benchmark when you are running it without any extra tools. It estimates background power consumption. So during each test, first it takes like half a minute to measure background power consumption, so power consumption of everything not related to NPU. And then it starts to run inference on NPU, and it measures overall power consumption. So it's NPU plus background. And then, since you already know what is the background power consumption, you can estimate pure power consumption of the NPU. We've checked whether, well, for the devices that we have in the lab, we are also doing 2 extra tests. One test is we are just fully loading, fully charging the device and just run the model internally until the battery discharges completely. And by knowing the capacity of the battery, we know what was the power consumption, what was average power consumption during the entire process. And second option, we are just measuring power values directly by connecting to the battery, and we are getting the source values. And like on all devices that we own in the lab, we got pretty much the same values for all 3 options. So like the results that we published on the website, these are the results that we obtained ourselves in the lab by doing these 3 measurements. So the devices, depending on what device you have, the values might be more or less accurate, but yeah. Overall, if you are doing power consumption measurement yourself, just make sure that you're enabling airplane mode, so all Wi-Fi, network, everything is disabled. So because sometimes the device might decide to download or upload something. To just avoid these cases, you're just enabling airplane mode, and all radios are turned off. And then you should also disable automatic screen brightness adjustment, and we also recommend to go to the minimal brightness as possible, also to remove this effect from the power consumption values. So in this case, the values that you will be getting, they would be pretty accurate as long as numerical power consumption values, numerical current and voltage values that are provided through API, if they are accurate. And on the majority of devices, we see that everything works pretty good. Well, there are some cases that we had some devices where these values were not making sense, but this happens quite rarely, and you can actually see this just from the power consumption graph. So sometimes you can just see that power consumption values, they do not correspond to actually load, to current AI workload, and it's quite easy to notice this. And in this case, the FPS per watt values won't make much sense, but you'll see this yourself. Okay, I hope that this provides an answer to your question. Are there any other questions? Okay, great.
Yeah, sorry.
Okay,
I do.
okay. Yes.
I do have one more. Thank you. That did answer my question. The way in which people in the conference ask questions is a little bit inconvenient. We have to walk up to the stand. But one more question I did have is about the pros and cons you mentioned between Executorch versus TF Lite, or Lite RT. I understand that analysis is kind of based on the trade-offs today. I'm curious what your take is on like the comparison between the two going forward. So what I kind of mean by that is, I guess, Executorch have an advantage in that they have deep integration with PyTorch being under the same team. Android and TF Lite or Lite RT or whatever, they obviously have some integration partnership advantage thing going on. Basically, I'm just trying to ask, like, where do you think it plays out? I know Meta are already trying to push on Executorch. Who do you think is going to win? Why? Blah blah blah.
Well, for us, it's a little bit difficult to say because it does not depend on us. So we do not establish the targets for Executorch teams. We just know that they were provided with feedback from the vendors, and they were provided with feedback from us also directly and indirectly. The situation is that for Lite RT, well, you saw that Lite RT got rebranding from TF Lite to Lite RT just because this was the only way technically to survive for them. Because since they previously supported only TensorFlow and no one is really using TensorFlow right now, the popularity of TensorFlow Lite also was decreasing because it was impractical just to do all initial development in PyTorch and then do implementation of the model in TensorFlow, convert the all weights, and it was just impossible for complex architectures. So because of this, TF Lite team, it actually understood that they have to support PyTorch natively. And that because this became one of their key priorities. And this is the thing that is making them alive. So you can expect that they are spending quite a lot of their efforts on bringing support for PyTorch. And as we've already tested, this support is actually quite good. So like almost all standard fusion architectures, they can be converted without issues from PyTorch to Lite RT. And here we're getting advantage of Lite RT because it's 8 years old. And all vendors support this support LightOfT pretty much natively because this support was happening for years, and pretty much any vendor who had NPUs, especially vendors who are dealing with smartphones, initially this was their first option that they had to support many years ago, and they continued to improve the support, continued to improve the drivers, continued to improve the delegates for this pathway. And therefore, right now, if we're talking, for instance, about whatever Qualcomm, MediaTek, Samsung, about Google, their drivers for the integration of their drivers into TF Lite, it was like pretty much good because all major issues they were solved during the previous years. And this is not the case that we see with ExecuteTorch. So since this integration just appeared, like this support for this ExecuteTorch delegates, it was added just recently. There was simply even not enough time to debug and develop everything. So we expect that like at best some time would happen till the moment when this support actually works even in the current setup. And yeah, so this is our ideas as for what's happening with ExecuteTorch and with TF Lite. So ourselves, after trying ExecuteTorch, we got not happy because we are not happy about pretty much all things. We are not happy about the things that you do not have pre-built binaries. We are not happy about the things that you need to convert model for each specific platform. We are not happy about things that the converted model cannot be executed on other platforms. We are not happy about the things that, again, even if you're trying to run the models on NPUs, you're getting lots of extra issues because this integration between ExecuteTorch and some drivers, yeah, it's just new and probably like 2-3 years should pass till it works as expected. And the same actually, it's not only this does not only apply to ExecuteTorch. For instance, you can see that we've mentioned that now a benchmark, Python A benchmark, for instance, it supports Qualcomm platforms through Onyx, QNAP delegate, and we didn't show you the results. And there is a good reason why we didn't show you these results, because the situation here is the same with ExecuteTorch, because this is a new integration and it apparently has some issues when you try to deploy the models, because it's not yet tested, and like quite a lot of time should pass till the moment when all layers are properly passed through your initial framework to acceleration framework. Since they collaborate, they communicate properly with each other, and since all small bugs are fixed. So we think the same about ExecuteTorch, and honestly speaking, we will be extremely happy if we run and if, like, say, next year, we'll be able to tell you that finally everything got changed and you can just use ExecuteTorch and you can run the models across all platforms and there are no issues, no acceleration problems. We would be extremely happy to tell you this, because we really, like, from our side, we are happy when there are multiple alternatives, multiple ways to accelerate the models, and when you can switch between them depending on which option is better for you, which option is more convenient for you. So we would be really happy to be mistaken here and like to tell you next year that we were completely wrong about everything that works here and that it works like a charm and you should use ExecuteTorch whenever it's possible. Yeah. Right now, we cannot yet say this, and if this changes, you'll hear this from our side. You'll hear this updates from us. And probably you'll also hear this from other vendors. So, okay, so are we done with the questions? Okay, so I think that we should really move to the presentation from MediaTek, because we're extremely sorry about the delay, because the guys had to wait for till the end of the presentation for almost half an hour. So now we move to the presentation from MediaTek. The topic is recent mobile AI advances and case studies. And the presentation would be given by three MediaTek guys, three very experienced guys from MediaTek. The presentation will start with a talk by Jimin Cheng, who is a senior manager at MediaTek Computing and Artificial Intelligence. I guess I even see you 1 second. Okay, I've made you a co-host and you can start sharing your slides.
Can you hear me, everyone online?
Mm-hmm.
Or should we take a break or just start it continuously? Yeah, if everyone is okay, then I will start my presentation. Because I have to share my slides from my desktop, so let me check this work.
Yes.
Yeah. Let me check. One.
Great. We can see it and we can hear you.
Yeah, good. Okay. So, let me check the presentation slides. Maybe to change. This one. Suppose the presentation screen should be full screen.
It's not yet full screen.
Yeah, I try to share with full screen, but the size here shows like.
Well, I mean, we can still see the slides quite nicely. So if you cannot enter full screen, it's also not a problem because everything we can see everything quite clearly, and it's not distracting.
Okay. Okay. Here, mainly focus this. When it's there, oh, this one. Yeah, let's try it like that. And now, and now do. Oh no, not that one. Still small. And I'll bring just with this is share, right? Yes. Okay. No, right. That's right. If not, we can bring that. Oh, the whole thing, yes, this photo. One second. Yes. Okay. Good. Thank you. Thank you so much. Technical problem. Sorry about that. Okay, this is my title about the mobile AI advances and some case studies to share with us, with all of us. And I'm the first presenter, Jiamin Zheng, and we have two research leaders, Hao Yuchen and Youxuan Xu, will share the case study parts. So for the first part, I would like to share some MediaTek mobile AI technology overview. And this slide summarize our achievement, key technology. For the achievement, the NPU power small name, 500 million intelligent devices, including smartphone, TV, surveillance, auto, and AIoT devices. And the neural pilot ecosystem has over 1,000 registered developers, and it is continuous growing. And our application cover camera, voice, display, gaming, communication system, control, and the generative AI. So here's some key technology showing here that we have a superior NPU hardware IPs. It shows the most performance and power efficient architecture, and it's transformer ready. And we have advanced NeuroPilot platform. It supports platform-aware optimization toolkits and also intelligent scheduler for multitasking AI. And we also provide the system optimization for best user experience. That means the NPU tightly coupled design for CPU, GPU, ISP display, and of course for that, things like that are the computing systems. And we also have CV engine for pre-processing or post-processing the images. Okay. And the button shows our NPU generations from starting from 2018, and from now it's Harriet P19 NPU2, the second generation in 2018, and generation to generation to now is the 9500 is NPU9 this year. So it's overall of our NPU hardware IP and the software development toolkits. The blue figures here shows the AI application is on the top level, and the middle block shows the NeuroPilot SDK and tools, and the bottom there is our coupled with our NPU. So this slide shows the NeuroPilot is a user-friendly SDK to develop AI applications. So NeuroPilot designed for developers to easily deploy AI models and run efficiently on MediaTek NPUs. Some key features shown here that include SDK that support major AI frameworks and the platform-aware optimization tool. And the second is the generative AI toolkits that is for developers to deploy generative AI models according to application requirements, such as customized optimization of accuracy, performance, power trade-offs. And we also provide the intelligent scheduler for multitasking AI. This shows the deployment process. For example, this generative AI toolkits supports the latest LLM, stable diffusion, or large multimodality models, or generative AI tech like LoRa, speculative decoding, and this is NeuroPilot SDK tool that will support the optimization for neural architecture search, validation, pruning, conversion, and also AI compiler. And so this is a runtime part. We have several generative AI applications like Magic Eraser, text summary, voice assistant through the NPU NeuroPilot runtime to run on NPU, GPU, and CPU, and for our products. Yeah, this is a NeuroPilot platform for our system. Yeah. And we have rich AI features with NPU that customers have landed over 431 AI features in 2024, and we'll have 542 AI features in this year. So this including for mobile, like camera AI, generative AI, AI eraser, magic rewrite, code text summarization, And we also have some customer product like automotive AI assistant, AI TV agent, and the smart home gateway. We have some demos showing different showcase. Okay. That's a quick summary for our NPU applications. Yeah. And this slide shows that AI technology trend is about the from the conversation AI like GPT-4, DeepSeek R1, V3 in 2024. It's rapidly growing and evolution to reasoning AI like GPT-01, 03, DeepSeek R1 in 2025 this year. And we can see the trend about test time computing is so popular, including this CVPR. Also talk about test time computing for computer vision. So we have some like language is like channel so inference to generate immediate prompts that improve to the final answer to raise the accuracy or reasoning. We will show some case on mobile data. And also for vision, it's inference to generate visual reasoning, iterative refinement, or self-consistency sampling during evaluation enhance prediction accuracy and improve the quality of vision task outputs. So MediaTek provides competitive inference hardware and software solutions. So we have some experience and we will maybe later we will show some case in this part, more technical part. And sorry, for this one. And this is the final page of my presentation that we have reached research collaboration and talent cultivations from the top level, the application, including the generative AI on the edge devices and embodied vision and the computational photography, autonomous driving and the ADAS and the cockpit, smart cockpit. And we also have the edge cloud collaboration and the embedded AI, including the vision language action foundation models, how to deploy on our devices. And we develop our own machine learning core for low bit representation for edge intelligent efficient representation for generative AI on edge devices. And the new foundation models architecture like Mamba. And we have a technical power talk about the Mamba vision. So you can expect that very good presentation later. And we also have AI compiler optimization, including TBM, MLIR, Falcon ML, and the multi-core computing technology, and the compiler scale-up technology. And for hardware parts, we have some collaboration and talent cultivation on NPU multi-core scalability, compression, deep compression for edge devices, and also computing memory and processing memory. Yeah, it's a very overview of our research collaboration and talent cultivations. And next, we would like to show two case studies. The first one will be the reasoning LM demo on D94,000 by Howie. And then the second case study is all around scan vision Mamba by Yushen. So let's go to the technical part. So how can you show your slides? Or
okay.
Okay, cool.
I will share. So I need stop sharing and I get the screen.
Okay. Cool.
Wait a minute.
So how will you show first?
Yes. Sorry. Can you hear my voice?
Yeah.
Okay. And then Butter Sir help me present the slide. Wait a minute.
I need to some time, maybe 1 minute to reopen the Google Chrome to share. Sorry.
Or I can share, or I will share from here.
Also okay. Yeah. Yeah, MAI 2025. Yeah.
No, I think no.
Sorry, not this one. Sorry.
Oh.
Yes. Okay, then I start my presentation. And hello everyone, and I'm Haoyun Chen from MediaTek, and I'm a senior AI algorithm engineer from MTK. And today I'm representing our team to share progress and some live demo of the LLM reasoning model and deploy on MediaTek Dimensity platform. Okay, so this work is printing from me and Bo Xiang. Okay, so the first page is the introduction page. First, I want to introduce that the MediaTek latest generation Dimensity chip is the Dimensity 9400. And this chip is, has achieved 3 remarkable milestones in LLM deployment. So first, the native NPU, named the Neural Processing Unit, can run LLMs with up to the 10 billions of parameters, and also including popular series such like the Llama and Qwen, Gamma, and more LLM or SLM. Okay, and this corresponds to my first plugin and a powerful AI accelerator. Okay, and second, it can also run the quantized model and lower to 4-bit weight, trying to meet the requirement of the end user, and including both good encoding and decoding speed and low power consumption. Yeah. Okay, and the third one is the support for long context input output, which means that it can handle long context requirement with up to 10,000 of tokens. Yeah, and which can better accommodate in the reasoning model inference output. So using the Dimensity chip can better represent or better show the reasoning models on the progress of its reasoning process. Yeah. And here I would also like to introduce the latest reasoning model, which got two major party, and one of it is the OpenAI. And sorry. Okay, and one of the parties is OpenAI, and which mainly include the closed source of model, and like a 01, 03, or the minimum one, 03 minute. Okay, and the other party is like the DeepSeek, and it got the open source model like the R1, and SLM part is the R1 distill Llama 8B and R1 distill Qwen 3B. And the distill Llama 8B and Qwen 3B is most suitable to be run on the edge, since the parameter is lower than 10 billions. Yeah. Okay, can you help me to change to next page? Okay, so in this page, we have chosen a classic conditional probability problem, which named a Monty Hole problem. And the key to solve this problem lies in understanding the probability change when switching doors versus not switching doors. So again, sorry. Okay, so you can see the slide. There are 3 doors, and one of the door got a car, and the other door got goat. Okay, so if the host tell you, given that one door is known to have a goat behind it, we aim to showcase the difference in output with and without using the reasoning model. Okay. So we can go to the next page. Okay, so in this page, we'll try to demonstrate the difference between the non-reasoning model and the reasoning model. So the video on the left side shows the open source Llama 3 8 billion, while the video on the right features the DeepSeek Distill Llama 3 8 billion. Okay, so yeah. So the video is automatically play, and audience you can check like the process between the left side and right side. Okay, so when prompting with the Monty Hall problem, you can see that the non-reasoning model largely lacks reasoning process, or we name that the human thinking process. And the non-reasoning model got the response with intuitively with the formulation and answer. So with the lacking of the reasoning process, it arrived the incorrect answer, like the 1/2. Okay, so on the right side, the reasoning model can be able to unfold. Yeah, okay, so the right side, the reasoning model can be able to unfold all the conditional probability and can be step by step. So it can finally get the answer to be the 2/3. Yeah. So okay, this presentation is so my presentation only got this 3 page, and this is concludes my report today. So can feel free to ask any question. Yeah, for the reasoning model deployment on Dimensity platform. Okay, is there any question?
Maybe now, so we can change to the next.
Okay.
The vision number.
Okay, thanks.
Could CM please share the screen of the PowerPoint? Thank you. It seems I could CM help to share the PowerPoint. I can share by my side.
Yeah, I just you the screen shows yeah
Close.
just yeah maybe you can
it's okay for this.
It's okay, yeah.
Okay,
Yes.
and the second case study is about all-around scan vision member. And we tried vision member because it is a new trend vision backbone, which transfer vanilla member into a vision backbone to extract features. Vision member can capture global image information with the linear complexity, rather than vision transformer, which need quadratic complexity. And the key idea to involve member in vision member is to transfer two-dimension feature maps into a flattened one-dimension sequence using spatial scanning process like 2D scanning. And we do some experiments. Oh, here is some experiments shows that the respective field of vision member can be long range, and capture long-range information. But when we convert an image into a one-dimensional sequence, some special adjacent pixels may become widespread, leading to an issue we call local pixel forgetting. For example, pixels that are adjacent along the diagonal direction can become excessively distant from each other during 2D scan, like the feature shows here. And we try to using various scanning strategy to capture diverse spatial information through different sequence. And we try some different scan like 2D scan, diagonal scan, zigzag scan, and Z-order scan, Hilbert scan here. And we try to combine two of them or multiple of them to capture complementary spatial information that are often missed by using a single scanning method. And we try some experiments on different image restoration tasks. Here is a result of real-world super resolution, real SR. We can see that our results are more clear than the previous vision transformer like Restomer and member IR and V-member IR, which only use a single direction scanning. And here's some results for real-world denoising on SIDD dataset. We can see that our results more clear than the others. And here is some motion deblur results. Here shows that our output is more clear than the other by we show the difference map below it. The last one task is dehazing. We can clear the haze more clear. This is an indoor scenario task, and this is outdoor task. In general, our experience shows that our all-around scanning can improve members' image quality to beat some vision transformer models. And this is the showing about second case study. Is there any question?
Okay, so if you have questions, you can also write your questions either in the chat or if you are attending the CVPR conference in place, you can come and ask your question using the provided microphone. Yeah, from my side, I should say really thanks for this presentation because they really are on topic and they show what can be done on mobile devices. And I especially liked your example with multi-hole. Yeah, it was actually a clever one to showcase the differences. And yeah, for attendees, you can see that you can even run 8 billion 4-bit quantized llama on domestic platform. So it's not about just very small models. No, you can just use really huge networks. And you can see how they just run on your NPU, on smartphone NPU.
You go back. Go back.
Maybe you have to speak here and for the
Can you go back again to the slide where the scanning line,
Scanner.
the
Okay.
flat?
Vision.
Okay.
Just share the vision member part.
This one.
We can see your slides now. Okay. Hello, Eugene. Are you showing your slides now?
Okay. I'm not sharing.
We can see your slides. Yeah. Just try again.
Here.
Oh, yes.
Yeah.
Yeah.
Okay.
Yeah.
So there is a question about the scanning process strategy.
You decide which strategy to apply.
Can you
So-
say more about your strategy, how to apply, and yeah,
Oh,
is that your question?
How do you decide? How do you
How do you design and measure?
oh, these scanning strategy are origin in previous work. So just one difference is we try to combine multiple scanning rather than single one. I think each single one can lead some local pixel issue.
How many did you combine?
So how many did you combine?
And for different tasks, we combine different numbers of scanning. For example, real SR, we combine 2D scan and diagonal scan. For the hazing, we maybe combine 2D, diagonal, and Hilbert. So maybe case by case to get the better performance.
And the combination, did you run several models and done that in parallel, or how did or concatenated the patching?
Like here, we only scanning on different scanning are processed, and we concat the output in the end of SSM function.
Thank you very much.
One question from me. Was this architecture designed with the neural processor in mind, or was this a theoretical work?
The architecture we reference some previous work like here, member IR. Sorry, the reference link may be wrong, but member IR is one paper of 2024, maybe ICCV or others. I just not remember.
And was this running on the edge device, or was this running within PyTorch?
The original is run on the PyTorch, and we tried run it on our MediaTek NPU. But we are tuning its performance, so I maybe not sure the final latency.
I see. So would there potentially be a trade-off between the architecture and the efficiency of it on the edge device?
Yes, and because member may be a linear complexity rather than quadratic, so we think it may be a probability to be an efficient model and handle image restoration tasks.
Okay, thank you very much.
Is there any other questions? maybe I stop sharing. Thank one.
If there's no more question, then we can figure out if you want to discuss more or explore more, exploration more questions, and then we can talk after the meeting. Yeah, welcome.
Anyways, thanks a lot, guys, for the presentations. So, like, I personally like them, like your presentation, and yeah, nice examples and a very good intro talk. Because I mean, don't forget that some of the challenge participants would actually have to design super resolution models for the Dimensity platform that was mentioned, for Dimensity 4. And yeah, for you, it's for those participants who are going to do this, this would be a very good intro. But yeah, also, like, again, for those who are watching us and for those who will be watching us on YouTube later on, this is a real example of running complex architectures on recent NPUs. So right now you can do something that was not possible just a few years ago. So a few years ago, no one could actually be able or would even think about like running 8 billion Llama model on smartphone or running stable diffusion model on smartphone. Right now you can do this. Well, probably you'll need some extra optimizations, but nevertheless, you can run very complex architectures on NPUs, and you see how much time and how much efforts actually the teams, well, in particular a team from MediaTek, spends on making everything possible. Because, okay, on also from my side, just it's hard to tell you how much actually engineering effort and how much work should be done to optimize the drivers and to like make sure that all these complex architectures or models, they can really be executed on NPUs that can be executed efficiently, that all operators are not falling back to CPU and you're getting the best performance. So this is really dramatic and very, it's enormous work, great work that is done by engineering teams, and that is done particularly by engineering teams in MediaTek. Because yeah, you see that it's possible to run these models, and I pretty much expect that next year we might see even more great demos from MediaTek with new models with even more complicated architectures, especially when it comes to new chipsets that will be released by MediaTek later on. So okay, so thanks a lot, guys, for the presentation. And now we are moving to the next presentation of the challenge results. So the presentation of the previous quantized image super resolution challenge. I'll start showing the slides. Okay, can you see the slides? And can you hear me? Okay, can anyone confirm that you can hear me?
Yeah, all good. We can see the slides and we can hear you.
Okay, great. So yes, so right now we'll talk about quantized image super resolution challenge that has ended together with the previous mobile AI competition, not the ongoing ones, but the ones that finished in conjunction with CVPR. So the task here is pretty much the same as always. We want to super resolve our low input images, and this task is used right now on numerous devices on numerous platforms, and it's needed for upstreaming, for upsampling low resolution media that is available on various platforms for telephoto conferencing, for video streaming services for instance, video conferencing, for instance, right now in Zoom, like for many sources like this, you actually need to do image enhancement and you need to improve the resolution of the data coming from the camera. Also, you can find pure photo super resolution models in the recent telephoto cameras, where basically, besides just using telephoto sensors, telephoto lenses, you also do vendors are also doing extra image upsampling by using neural networks. So going beyond 3x or 5x zoom and introducing an extra magnification factor, but it's done not by just linear or by cubic image resizing, but instead it's done by applying efficient super resolution models, efficient super resolution AI-based models. And here the task was same as in the previous competitions. So basically 3 times image upsampling, you need to achieve pretty much real-time performance on mobile NPUs, and the models should be fully quantized so that they can run efficiently and they can run fast on recent smartphone NPUs. As always, we use the same dataset. It's div2k, a very popular dataset that is used for benchmarking almost all current image super resolution models, and it provides you with a large number of images and quite diverse content. The target in this competition, in terms of in terms of estimating the quality of the reconstructed images, we used the standard PSNI and SSIM scores. And for runtime, we used Google Tensor chipset with Google Tensor processor with Google Tensor GPU. And also the runtime of all solutions were evaluated on this chipset. And yeah, I should mention that the participants had actually quite bad times when running their models on Google Tensor chipset, because unlike MediaTek and Qualcomm that have very, very good delegates, very, very good solutions for running models on the NPUs, we cannot say the same about Google Tensor chipset. As a matter of fact, it's a little bit disastrous, the situation with them. So, and this is something that the participants saw quite well, because we had a couple of cases when the guys were changing just one layer in the model, or even not one layer, they were just changing the order of the layer. And we saw that, for instance, on other platforms, this was not affecting the runtime at all. So the runtime was remaining the same, and the runtime should not be changed in this case. But in case of Google Tensor, the runtime was changed by a factor of 2 or 4, because even these small changes, they resulted in completely different execution graphs. And all in all, the participants were just getting very, very different runtime results for the models that looked pretty much the same and that were showing pretty much the same runtime numbers. So unfortunately, we can say that driver support and the execution provider for Google Tensor TPU, it's not major, and it's not really good if you want to deploy something on these smartphones. So this is the current state. And yeah, so the participants of the challenges, they actually had to deal with this stuff, and I'm pretty sure that they got some experience and they actually saw the difficulty of working with this kind of TPUs, this kind of NPUs, and actually the situation with IoT NPUs would even be more complicated and would be even worse here. So it's with Google Tensor GPU, it's not the worst case that they might see. With some other platforms, it will be even more complicated. And therefore, it's so important to work directly with your target evaluation platform, because again, on the paper, your model can be very optimal. Everything should be running smoothly, so you have small number of layers, all layers are compact. When you test this model on CPU or GPU, everything is just works perfectly. Here you have a real case scenario. You have an NPU, you just change the order of 2 layers and the runtime is increasing by a factor of 4. So this is what you can get quite often when working with diverse NPUs. And yeah, this is the case what we had here. So for local evaluation, the guys used a benchmark application that was mentioned during the introductory talk, and for final evaluation, we use the same setup. Here you can see the final results obtained in this challenge. So what should be noted is that despite the complexity of the task, pretty much all participants were able to provide very efficient solutions. So all models, pretty much all models had demonstrated a runtime less than 60 milliseconds on the NPU or Google Tensor NPU. And this means that, and yeah, for majority of them, the results were very close to real-time processing when upscaling videos to full HD resolution. The best, well, and you can also see that all models were pretty much compact. So the size was less than 100 kilobytes for almost all of them, except for one solution. And you can also see that in this particular case, almost all guys used Keras and TensorFlow. And the reason for this is that quantized ware training and post-training quantization is, well, it's a little bit easier to work with Keras and with TensorFlow. With PyTorch, it's also possible to quantize the models. Also, it's possible to quantize with built-in lighter T quantization tools. It also supports PyTorch framework, but it's a little bit more trickier now. And since the majority of the participants had previous experience working with Keras, they just decided to use Keras. So yeah, so the results, yeah, the challenge winner is Team Antasar, and well, they were able to achieve just dramatic results on Google Tensor NPU, so almost only 12 milliseconds per one inference. So this is quite impressive, and this gives us FPS more than 80 FPS if you're running this model continuously. And the second best solution was provided by Team Z6. And actually, this team was our challenge winner 3 years ago. It should be mentioned that, yeah, both models, they show quite nice results, quite nice PS around the same scores. So this means they significantly outperform the bicubic baseline. So, I mean, the solutions, they work simply much better than just bicubic upsampling. And still, even on Google Pixel NPU, they can demonstrate very good results. Now imagine if we are switching, for instance, from Google Tensor NPU to MediaTek Dimensity 9400 or to Qualcomm 8 Elite. In this case, you can expect that the runtime would be pretty much close to just 2 or 3 milliseconds, and this is rarely the case. So their designed models are extremely efficient. And now let's just look at what both teams presented. So Team Antasar presented quite shallow architecture, very small network. And the key idea here was to use layer reparameterization. So all these blocks, during the training, they consist of multiple convolutions. And during the inference, they are fused into one single 3x3 convolution. And this gives you quite extra benefits in terms of the fidelity of that the model can demonstrate. Also, the guys used skip connection. It was really helpful to mitigate the issues caused or accuracy loss caused by model quantization, and they used quantized training. So not only just post-training quantization, but also quantized aware training to reduce loss caused by model quantization. And by the way, as we can see on the slide, the loss, the accuracy drop was really minimal. So it was more than 0.1 dB in all cases, and in case of underside, it was just 0.08 dB, despite the fact that the model is very, very shallow. And the shallower is your models, usually the bigger accuracy drop you have if you are quantizing the model. So yes, and yeah, and one loss was used for model training. So all in all, by getting a solution that is very tiny, that demonstrates great results, that can run pretty much on any NPU, because since it consists only of few convolutions, one skip connection and depth to space layer, pretty much any framework would support it. So it's a very, very practical model, and it demonstrates already very good results. So it can actually be used as a baseline for any super resolution tool, and it actually might be even more efficient and faster than by using just by keeping image upsample. And the second solution produced by team Z6, it was using pretty much same ideas. So it proposed to this processing was happening into different blocks in recursive concatenation and enhancement in residual, enhanced, and feature extraction blocks. Again, this team, same as previous one, used skip connections for reducing the accuracy loss caused by quantization and quantized layer training. So, and they trained the model in 3 steps, in 3 stages, and altered the loss functions, learning rates, and other parameters. So to be able to achieve a higher result, despite the fact that this model is also very small. You can find a detailed description of these solutions and all other solutions proposed in the competition in the paper, in the challenge paper. So they, as far as I can see, they became available just yesterday, these papers. So you can now access them through CVPR website, and you can just download all of them. And here is, if you use this QR code, you can just access this paper directly. And it provides you with much more details about both solutions, about allegations, and about all other models. So yeah, thank you for your attention, and we can now. So any questions? Okay, so in this case, we move directly to the next talk. The next presentation would be given by ZT, and I saw there one moment. I will unmute you. Oh, no, not unmute you. I'll make you co-host. Okay, and they will present top solutions that was achieved in video super resolution challenge. And yeah, they will describe the model that was developed for efficient video super resolution on mobile devices. Yeah, we can already see your screen.
Can listen to me?
Yes, we can hear you.
Because of my bad oral English, so
No, it's fine. We can all understand you. And yeah, we can see the presentation, so we can start.
Okay. Let's let my AI agent to introduce our work.
Thanks to the invitation of Mobile AI Workshop, we participated in the Video Super Resolution Challenge on the actual mobile accelerator and submitted a paper named RepNet VS, our reparameterizable architecture for high-fidelity video super resolution. We are from State Key Laboratory of Mobile Network and Mobile Multimedia Technology, STE Corporation. Video super resolution is one of the key computer vision tasks, restoring high-resolution image frames from their low resolution. The degradation is B-cubic downsampling, and 4 times super resolution is achieved fidelity quantified by PSNR and operational efficiency measured through end-to-end latency, requiring solutions to be able to balance accuracy efficiency. The final score for this challenge is determined by two key metrics: model runtime performance on the target MediaTek APU method. We use NAS search to search for the best parameter configuration between PSNR and flops. We employ 1x1 convolutional layers for dimension reduction, enhancing computational efficiency while preserving feature representation capabilities. Multi-level feature fusion via channel concatenation enhances representational capacity by combining low-level textures and high-level semantics. We enhance the representation capabilities of network through structural reparameterization, using more complex networks during training and merging them into a common convolution during inference to optimize representation capabilities and computational efficiency. Network architecture: we propose RetNet-BS, array parameterizable architecture. This approach specifically addresses the identified computational bottlenecks while maintaining reconstruction fidelity through multi-level feature fusion. As shown in figure, we use channel concatenation to integrate multi-level features of deep and shallow network layers to enhance the feature representation capability of the model. To optimize computational efficiency, we incorporate 1x1 convolutional layers for dimensionality reduction throughout the fusion process. Specifically, prior to the depth-to-space operation, we substitute conventional 3x3 convolutions with 1x1 convolutions to achieve efficient channel compression from 48 to 3 dimensions. This architectural modification can speed up upsampling by a factor of 4 while improving reconstructio quality. Reparameterization. Reparameterization is a technique in neural network design where models employ intricate architectures during training phase, e.g., multi-branch with parallel operations that are subsequently transformed into equivalent but computationally efficient structures during deployment. The proposed reparameterization module adopts a sequential architecture comprising 3 key operations. Initially, a LX1 convolutional layer expands the channel dimension by a factor of 4, followed by a 3x3 convolutional layer that extracts spatial features in this elevated feature space. Subsequently, a LX1 convolutional layer reduces the channel dimension back to its original size, completing the bottleneck structure. In order to maintain dimensionality consistency, a residual connection is implemented using LX1 convolution. Design search space. To achieve the best balance between reconstruction quality and runtime efficiency, we use FNAS to automatically search between reparameterized modules and channels. The search space presented in table was systematically established with a focused exploration of channel count variations and reparameterized module quantities to identify optimal parameter configurations within the proposed architectural framework. Identity optimal parameter configurations within the proposed architectural framework. We employ a two-phase training strategy. During the initial phase, neural architecture search NAS is utilized to conduct preliminary parameter optimization regarding channel quantities and the number of reparameterization modules. Subsequently, we initialize the model with parameters from the preceding phase and perform fine-tuning using an L to norm loss function for enhanced performance refinement. Experimental results indicate that the optimal configuration under the proposed architecture occurs with 16 channels and 4 reparameterization modules. Result: our proposed RetNet-SAR algorithm was evaluated against B-cubic interpolation, Ethernet, and our CBSR. From table, it can still achieve a better quality efficiency trade-off despite longer queue runtime. Visual comparison. vision in terms of subjective visual quality, with comparative results demonstrating its significant superiority in perceptual performance, as shown in figure. Conclusion. In this paper, we introduce RepNet VSR, a reparameterizable architecture designed to optimize inference efficiency while maintaining high restoration quality in video super resolution. We will further study the characteristics of video super resolution. Thanks to the
Thank you. That's all.
Thanks a lot for the presentation. So, yet another work that tells about efficient solutions that can run on real devices. And in this case, actually, it's also MediaTek Dimensity NPU. So I'll see it for the third time today. Okay, so any questions from the participants? Okay, so if we don't have too many questions, yeah, I think that for the participants who are watching us on site at CVPR, it's a little bit difficult to ask questions. Yeah, so if there are no questions, then we're moving to the next presentation, the space paper presentation from Samsung. And the topic is CDVS, compressed domain on device memory efficient 8K video slow motion. And the talk, I guess, will be given by Jin Lee. I think. Yep. We can see your presentation. We can see your slides. But we cannot hear you yet. There is no sound.
Can you hear right now?
Okay, yeah, we can hear you.
Okay, great. Okay, let me share my screen. Hi everyone, I'm Jin Lee. I work at MPI Lab at Samsung Research America. Today I'm going to introduce our research on the compressed domain on-device memory efficient 8K video slow-mo. We call it CDVS. So this is not some technology in current or future Samsung products. The talk will contain three parts, so a brief introduction and the compressed domain video slow-mo algorithm, and also a summary. So I think everybody are familiar with video, are using cameras, so taking videos. Like video processing is almost everywhere, and it's very important. It providing more information compared to the static image because it gives more temporal information, and it's very easily accessible as long as you have a phone with a camera. But it becomes more challenging with increase of the resolution. So what is video slow-mo? Video slow-mo is video slow motion. It's a temporal zoom to increase the frame rate so that you can have like the motion will become very slow. So it's widely used in sports, nature, and some other used cases. Right now, the current existing video slow-mo, at least on device, is low resolution. due to very limited compute capability. As currently, as all like image and videos goes higher and higher resolution, because the higher resolution will provide more information, it have more details and better image IQ. But it also requires a lot of computation memory and power, which for the on-device processing, it's very challenging because like the mobile devices usually have very limited computational resources and the power capacity is not that great compared to other devices, and which means the on-device video algorithms need to be very efficient and fast. On top of that, the video slow-mo is more challenging because it is expanding the videos, which requires a lot of more like memory efficiency. So how can we so currently on the market there is no like 8K video slow-mo available. So how can we achieve that? So I will discuss our solution about compressed domain videos 8K video slow-mo algorithm. So first, I will so this is an introduction about what is compressed domain. What is compressed domain video slow-mo? As we all know that the traditional slow-mo the traditional slow motion algorithms usually takes the value frames, do some AI blocks like optical flow estimation, occlusion mask estimation, and frame interpolation, and then generate the slow motion video. Instead, so what is compressed domain video slow-mo is instead of processing the video in video domain, we move all the AI blocks to the compressed domain, first of all, to save memory and also to reduce the complexity of each AI component. So this is the overview of our system. So given the video frames, the system contains two parts. It has an image compressed domain converter, which contains an encoder and decoder. The encoder will map the images to the compressed domain, and the decoder map it back to the image domain. And also it contains three AI blocks within the compressed domain. It's optical flow estimation, occlusion mask estimation, and frame interpolation. I'm going to introduce each component in the following slides. First is the image compressed domain converter. So here we use a very standard VQE style architecture. It's a unit structured network, and to save memory, we add the vector quantization. It is a hierarchy encoder. We have two levels of features. One higher resolution one to preserve the detail, and the lower resolution one to keep the semantic information. And overall, we can achieve 4 times compression compared to the original input image. So here is an result. On the left-hand side is the original image, and on the right-hand side is the output from the encoder-decoder. Compare these two images, we can see that the network can preserve the image detail even for the small tiny text, which is very important for the compressed domain, like for the latent space. Next is I will talk a little bit about each component briefly. So the first component is a compressed domain optical flow estimation. It has 2 steps. The first step is optical flow estimation from the so given 2 consequential frames. We first estimate the backward and forward optical flow. So here, instead of giving two frames as the input to the optical flow estimation, what we did is we feed the optical flow estimation network using the features extracted from the encoder. So the network architecture is a raft style model, and it takes the latent features as the input. Since our ultimate goal is to interpolate the intermediate frame, we need to interpolate to generate the intermediate frames. We just use linear interpolation to generate to estimate the intermediate optical flow. And then next is some results of the compressed domain optical flow estimation. So here on the right-hand side is given two consequential frames. We showed the pixel domain optical flow estimation results and the compressed domain flow estimation results. Visually, we can see that it has compatible accuracy, but with respect to the computational complexity, we do some profiling on the A100 GPU. It is almost 4 times less computation, but two times less computational time, and also it's more than 2.5 times less memory. Next is the occlusion mask estimation. We know that for the frame interpolation, occluded region is very challenging and difficult to handle. So in order to do that, we trained an implicit network for occlusion mask estimation, which takes the two bidirectional optical flow as the input and use a very simple unit structure. And the last component, AI component, will be the frame interpolation in the compressed domain. So here we call it frame interpolation. Actually, instead of generate the real frame, what we did is we generate the latent space, like the feature of the intermediate frame. This is a NavNet style network architecture. It takes the two warped image as the input, and also it's jointly trained with the occlusion mask network. So this is the overall system of our algorithm. So next I will show some results. In order to we do some objective metric comparison. We compare with the AMT video slow-mo algorithm, which is supposed to be the state of art. With respect to the objective metric, we compared the PSNR and SSM and tested on the Vimeo dataset. As we can see that our proposed model with respect to PSNR and SSM are better than the AMT model. And here is some visual results. So on the left-hand side, we put the 4K slow-mo result, intermediate frame results, and middle column is AMT results, and the right-hand side is the compressed domain video slow-mo results. As we can see that it's very clear that the 4K video is much worse compared to the 8K video. So the AMT and CDVS are the 8K video slow-mo, and on the very left column is the 4K slow-mo. And also on like the CDVS also preserves more detail and have less artifacts compared to the AMT. And this is here is the video results. We compare with a 4K slow-mo with a 8K slow-mo. We can see that the resolution and image details are much better. Since our goal is to run to have build a system that can run on the system. So we try to convert the model and try to run the whole system for the 8K video slow-mo on the mobile device, on the phone. So we were able to convert everything and run end-to-end of the 8K video slow-mo on the device. Here, this is a profiling of the system for 8K video slow-mo for 4x frame rate conversion. So on this table, you can see the computational time. So for a current implementation is not optimized. We just want to get everything working and worry about the optimization later. But it shows that our whole system for 8K video slow-mo is very efficient and hardware friendly, and it can be converted using the Qualcomm 2, and it's running on the mobile device. And we measure each component, the component level time consumption. So as a summary, so like high resolution video slow-mo on mobile device is very important and challenging. But by using the compressed domain technology, moving the AI blocks onto the compressed domain instead of the pixel domain, which makes the 8K video slow-mo possible on the mobile device. And the further system optimization can provide more memory and computational time benefit. Also, like as a future work, we are also considering generative algorithms to combine the compressed domain technology in order to have better mobile like applications. So yeah, that's my talk today. So, any questions?
Yeah, thanks a lot for the presentation. So, anyone has some questions? And while the guys are thinking, I have a question. So on the previous slide, when you demonstrated the runtime, this was the runtime on CPU or NPU?
On NPU.
NPU. Oh. So all blocks, all steps were compatible with NPU?
Yes.
Wow. Yeah, that's not bad for 8K videos.
Yeah. So we just like using the very basic conversion tool. So we haven't done any optimization yet.
Yeah, and this is quantized or floating point?
This is 16-bit float.
Oh yeah. So yeah, if you make it quantized, you'll have quite extra improvement.
Yes.
And what about Exynos chipsets?
Pardon?
What about Exynos chipsets?
Exynos
Exynos.
chipset?
Yeah, Exynos. In Samsung, you have Exynos chipsets.
We used to converted on the Qualcomm one.
Yeah,
we didn't.
Yes. Will you try to make it compatible with Exynos NPUs or no?
It should
Just
be.
curious.
It should be, because all the component AI component is have the basic layers, so it should be.
Okay. Yeah, but yeah, you should also optimize. You're working at Samsung, you probably need to optimize for Samsung hardware as well.
Yeah.
But yeah, the task and the results are really great. And I really hope that next year we'll see even better results in terms of like adaptation. that probably you won't be able to show us real-time demo. That
Sure.
is doing the same stuff, but on the device, and probably we won't be the first to see this demo. Maybe the users of the Samsung S series devices will be able to test this method first, maybe next generation Samsung phones.
Mhm.
Okay, if we don't have any other questions, then we move to the next talk. Well, actually, it's also a challenge presentation. Okay, so now we'll present the results of the Learn Smartphone ISP challenge that we also had with CVPR conference. Oh, now it's better. Yeah, so the task, I guess it's also familiar for everyone. We have raw wire data coming from camera sensor, and we want to transform these images into RGB photos. And yeah, we want this to do. So why do we want to do this task? Because technically we want to have one model that incorporates all ISP steps and just get the best possible results by using only one neural network applied to our original raw wire data. And the experiments show that we can actually get very decent solutions, and at least these solutions can be used as baselines for many ISP systems. So the goal in this challenge was to design an efficient model that can demonstrate good runtime on GPUs and that can also demonstrate good visual results. So you do not model not only run fast on GPUs, you also want to want the reconstructed images to be looking nice. So as for the dataset, the participants used the same Fujifilm Ultra ISP dataset that was used in the previous competitions. It consists of a large number of photos captured with Sony Exmor mobile camera sensor installed on MediaTek Dimensity development board, and the target photos were obtained using Fujifilm GFX 100 medium format camera with 102 megapixel camera, sensor, and the target images were just perfect in all aspects, including the dynamic range, resolution, color rendition, everything is ideal. So the performance of solutions was assessed using three metrics, the standard on PSNI SAM, and additionally, we also used mean opinion scores to check the perceptual quality of the images generated by models submitted by participants. The runtime of the models was estimated on the Snapdragon 8 Elite and the Dimensity 94 chipset. So the models running on the GPUs, it's Adreno GPU in the case of Snapdragon 8 Elite, and ARM Immortalis GPU in case of the Dimensity chipset. So the images, the models were reconstructed photos of full HD resolution. And yeah, for local runtime evaluation, the participants used a benchmark application. And since the results obtained on local GPUs are pretty much proportional to the results obtained on the target GPUs, it was quite easy to do all development just by using the benchmark and using your own device. Here you can see the results obtained in the challenges, and again, here you can see that almost all solutions were quite efficient. And in particular, we have the challenge winner team, Awesome Neural, was able to achieve a runtime of just 5 milliseconds on Adreno GPU. And you remember during the introductory talk, I told you that GPUs, they might be actually very performant when we run computer vision models. And if we're taking older generation GPUs, then in this case, we can actually get much better results than on NPUs. If we're running quite large architectures or just models that are doing image-to-image encasement. And here you can see that you can actually achieve the runtime less than 5 milliseconds when reconstructing full HD resolution image, and even without using an NPU. So GPU is actually a very powerful backbone that can generate that can do the inference really fast. And yeah, of course, in case of NPU, the inference here would be inference time here would be even smaller, but this is just a very nice example that if the model is implemented properly, then you can get really, really good runtimes even by just using GPUs. And the first two solutions, solution from Awesome Neural and DHT XSF Lab, they were not only fast, but what is even more important, they were quite performant. You can see that the PRCNR score in both cases was slightly above 24 dB. PRCNR score was, SAM score was greater than 0.85. So, and our visual checks demonstrated that the quality of the reconstructed images is more than satisfactory. So the solutions really can be used as backbones, as simple baseline models for performing image reconstruction, even on IoT platforms that have not very powerful GPUs, but considering the efficiency of the solutions, considering the model size that is less than 20 kilobytes in both cases, this is just a very, very perfect baseline models that can be used for RGB image reconstruction on pretty much any platform and pretty much on any NPU. Now we'll move, and yeah, here also you can see that the majority of teams used PyTorch, and since there was no need for model quantization, it was perfectly fine to just use lighter T conversion tool that was also mentioned earlier that allows you to convert PyTorch models to TensorFlow Lite format, and like almost none of the participants had any issues with this conversion, and this finally allowed them to do all development using PyTorch and not use any custom converters that convert PyTorch models to Keras and then converting Keras to TF Lite. Here everything was straightforward, and as you can see with these tools, it's possible to get really good results. So now discussing a little bit the solutions proposed by top teams. So the challenge winner, Awesome Neural, it proposed a very shallow architecture, nano-vision net architecture that is based on SciNet. And you can see that here it's pretty much an art of constructing small, tiny networks, because the model consists of only a few layers. But it's more about the composition of the layers and the composition of the blocks. Because despite of just using 3x3 and 1x1 convolutions and just having a few convolutions, again, the team was able to achieve a PSNR score of over 24 dB, which is really great. And this was achieved primarily by using an appropriate architecture. The guys also had channel attention mechanism, which is here, and this channel attention is very, very important for ISP and for image enhancement tasks, because it allows to play with image brightness with global parameters and sometimes even with color rendition. Because if you're using just convolutions, just pure convolution layers, they are sometimes not able to adjust the brightness correctly. And to do a proper white balancing, you really need to have something like channel attention or any other alternative operators. So here the guys use them, and this was one of the key features that allowed this model to achieve such good results. And yeah, so you can also see that the guys used parallel activations instead of normal rel or linear rel. That also improves the capacity of the model, and pixel shuffle for image upsampling instead of transpose convolution, because in this case you also have purely logical operator, and this saves you some time. This reduces the latency further. So this is a solution from Team Awesome Neural, and again, it's a very, very good baseline for this problem in general. And the second solution proposed by Team DHT XSF Lab can be seen on this slide. You can see that, yeah, in this case, we are dealing with much bigger model, but here the guys used a different trick. We saw it in the solutions from Image Super Resolution Challenge. So here the guys also used feature fusion. So the model had a number of diverse branch blocks, and you can see the architecture of which diverse branch block here. So it consists of many different convolutions to enhance multi-scale feature capturing, and later on, when you want to perform the inference, these layers are fused to this. And this ensures that the resulting model is quite compact and quite efficient. And here the guys also use channel attention and channel scale blocks, again, pretty much for the same purposes, that you cannot do proper white balancing without using some global layers that can adjust the content of all features. So, and this allowed, and yeah, also pixel shuffle on top that further reduce the latency. So pretty much standard ideas, but here we have also quite good implementation, which allowed this model to be both tiny after fusing all layers and to demonstrate very good results. So this paper, this challenge report is also available online. You can just scan this QR code and you'll be able to see a detailed description of all solutions, of the training strategies, of the architectures and the results. So I hope that you'll enjoy this paper. And now, so anyone has some questions? Okay, if there are no questions, then we're moving to the next paper presentation, which is Learned Lightweight Smartphone ISP with unpaired data, and it will be given by Andrei, and Andrei is present in person at CVPR, so I guess he will now connect from the main auditorium.
Okay,
good.
everybody.
Yes.
Everything is okay?
Yes, we can see and hear you.
Okay. Every high-quality smartphone image is the result of a complex and carefully tuned image signal processor pipeline. The output of the sensor goes through the ISP, which refines the data to produce visually pleasing results that are well suited to the human visual system. ISP transformations can be defined as a mapping from the raw image space characterized by a binary pattern color filter array to the RGB image space. Essentially, the functions that make up the ISP pipeline include demosaicing, denoising, white balance, color correction, tone mapping, gamma correction, and compression. Increasingly, the traditional carefully handcrafted ISP models on the ISP are being replaced or augmented by deep learning models. Notably, various neural networks have demonstrated their ability to approximate this complex transformation using paired data. In such cases, the network learns the mapping through direct correspondences between raw images and ground truth data captured with a professional camera with matching content. However, such approaches come with several drawbacks. In particular, when a new camera is released, a pre-trained neural-based ISP may struggle to accurately render the corresponding raw data. A common solution is to train or fine-tune the model on a newly created dataset, where raw images are captured using the newly released camera. To achieve good generalization and high-fidelity results, datasets should be sufficiently large and contain content that is aligned on the pixel level. In practice, this is a challenging task due to a wide range of factors that can lead to pixel misalignments, including slight changes in viewpoint and dynamic scene elements. Moreover, while specialized alignment algorithms often produce good performance, they can also produce several warping artifacts. One step further in this direction is to adopt a training strategy that does not rely on paired images. Working with unpaired data would imply using only datasets corresponding to the input and target domains. In this talk, I will present our work, a novel method for training lightweight ISP models suitable for running on smartphones using unpaired data. Our method achieves promising results across various configurations, including different neural network architectures, data distributions, and selection of parameters. Specifically, our experiments are conducted on Zurich Roto RGB and Fujifilm Ultra ISP datasets. We primarily use the compact network architecture proposed by the winner of the 2022 Mobile AI Challenge. This lightweight model consists of only 3 convolutional layers with 12 channels each, followed by a pixel shuffle layer, resulting in approximately 3,000 parameters. Despite its simplicity, the model delivered good performance, achieving runtime below 7 milliseconds on the competition platform GPU. Additionally, we employed a similar architecture with half number of parameters and a more complex model that achieved state-of-the-art performance in the 2024 on Fujifilm Trace dataset. Although fast inference is a priority, the training process is not constrained by the computational cost. Therefore, we incorporate additional networks for adversarial learning and feature extraction. Color, texture, and content attributes are captured through dedicated loss functions, each using embedded features extracted from different pre-trained networks. Additionally, a lot of variation loss is applied to promote spatial smoothness and suppress visual artifacts. To ensure structural consistency, the raw image is first demosaicked using a specialized algorithm. Both the resulting and target images are then converted to the lapse color space, and only the luminance channel is retained and replicated across the 3 RGB channels. The content loss is computed as the difference between feature activations extracted from the last convolutional layer of a pre-trained VGG19 network. Total variation loss penalizes large differences between adjacent pixels in both horizontal and vertical directions. To improve perceptual quality and color fidelity, we incorporate relativistic adversarial losses that compare real and generated images. Discriminator laws include gradient penalties for both real and generated samples to improve training stability. Meanwhile, the generator is trained to produce outputs that are perceived as more realistic than the real ones. Our method employs 3 discriminators. One for color, which receives features from the last hidden state of a pre-trained vision transformer, and 2 for texture, which receive a feature from linear activations following different convolutional layers of our LPIPS plus network. The total loss function is defined as a weighted sum of 4 components. Choosing appropriate coefficients for these loss terms is crucial, particularly when adversarial objectives are involved. To address this, we adopt a dynamic loss adaptation strategy. At each training step, the weights are computed such that the gradient norm of each loss component is normalized to 1 when it reaches the neural ISP. This ensures balanced contributions from all terms during optimization. Furthermore, the weight of the total variation loss is carefully adjusted to avoid oversmoothing. It is kept strong enough to suppress unwanted artifacts, but not so dominant that it causes the generated images to become blurry or lose important details. One of the texture discriminators receives features reaching low-level information, such as brightness and high-frequency details. While it helps preserve the structure, it may also introduce some noise. The second texture discriminator operates on feature from a deeper layer of LPIPS Plus, capturing higher level abstractions that enhance perceptual quality and help suppress this kind of noise produced by the first discriminator. Alongside the unpaired training strategy, we define a method that uses paired data, which serves as an upper bound for evaluating the performance of our unpaired approach. In our experiments, we apply this method both with and without the texture adversarial loss to highlight its influence and its potential in supervised training scenarios. Okay, this feature compares different models against the ground truth shown in the first column. we selected the images patches rich in high frequency details and textures such as field branches, building edges, and reflective water surfaces to provide a challenging evaluation. Models incorporating the adversarial texture component produce noticeably sharper and more detailed outputs, demonstrating superior performance in preserving fine details. In particular, the model trained in the unpaired setting produced sharper results compared to the one trained in the paired setting, but without adversarial losses. Here are presented full resolution comparisons between ground truth images and the outputs of the compact backbone model trained with paired and unpaired strategies. The examples demonstrate that despite its lightweight architecture, only 3,000 parameters, it effectively reproduces a variety of textures and a broad range of colors. Yes, key features such as a vibrant red of buildings, deep sky blues, natural greens, and fine structural details are all preserved. The model trained without pair supervision achieves visually compelling results, supporting its robustness and generalization capacity. On the Zurich Auto RGB dataset, the compact model achieves comparable efficiency in terms of pixel density, PSNR, and structural similarity across both pair and unpaired training strategies. In terms of perceptual quality, the unpaired model performs similarity to the paired model, trained without adversarial losses. The paired model with adversarial texture loss outperforms LAN in the LPIPS metric, although LAN reported the highest PSNR when introduced in 2022. On the Fujifilm Ultra high-speed dataset, all three backbones showed consistent performance across all evaluation metrics on both the local test set and the official validation data from this year edition of the contest. In particular, the unpaired method achieved a PSNR score within 0.3 decibels of the value reported by the winner of 2022 edition in the pair setting. We believe that our work can be helpful to others, so we have released all our code and the pre-trained models. Thank you.
Thanks a lot for the presentation. Any questions?
I have one question. Yeah, so thank you so much for your work and for your approach. I'm very familiar with your code. And I have one question. In your architecture, you have a branch with the demosaicing algorithm, and then you do some kind of demosaicing of the input image. Then you apply some matrix multiplication and you do some kind of white balance. And then after it, you transfer the image to the LAB color space, take luminance component, and then put it to the VGG neural network and can calculate the content loss. And my question is, how do you calculate the white balance factors to do the white balance manipulation and to do it this kind of operation? Because, for example, if you suppose if the data fully unpaired, you cannot compare. You do not have some paired examples. You don't able to calculate these factors.
The idea was to suppress the color information so that it focuses only on structural information to learn more stable and faster. That was the idea of these operations. I'm not entirely sure that I understood
Okay, so in the code in the your pipeline, you have demosaicing algorithm, and you have you're using like a Menon demosaicing algorithm, and you take an input buyer array, and then you do some kind of demosaicing, and after it you apply some operation which performs white balance operation. And to do this kind of operation, you use the matrix with the white balance factors. And you have different numbers and then you multiply the image using these different numbers which are hard-coded into the code. And after it, you put this image to the VGG neural network to connect to compute content loss. And
Yes.
the main, my question is, how do you get the numbers to multiply the image after the demosaicing algorithm?
The numbers are chosen empirically so that the colors are related to the natural view. So by hand, I choose the three values.
Okay, thank you.
Yeah. Thank you for your question.
Okay, do you have any other questions? Okay, if not, then we are moving to the next talk that would also be given by Samsung. The title of the talk is Compressed Domain Multi-Frame Processing, and the talk will be given by Cheng Yuan. And I see that you are online. Yeah, we can see the slides, but we cannot hear you.
Okay.
Yeah, now we can.
Hey everyone, my name is Cheng Wang, and I'll present our work, compressed domain multi-frame processing. So smartphones have smaller lenses and sensors compared to regular cameras. So as a result, less light reaches the aperture, noise is relatively high, and dynamic range is narrow. So to overcome the limitation caused by this, in smartphone cameras, multi-frame processing technology is applied. So it creates a single image by combining multiple images when the user hit the shutter button. It has become an essential component in mobile devices to reduce noise and improve dynamic range. Meanwhile, image resolution is increasing. People now can take, say, 200 megapixel images on smartphones. This poses challenges in image processing, especially multi-frame processing. So for example, if we consider 200 megapixel image, each raw frame takes around 400 megabytes to store if we assume 16-bit processing. And a demozaiced image will take more than 1 gigabyte. So it's almost impossible to run multi-frame processing in this case. Traditionally, we have image compression methods that tackle the problem of high memory demand, such as JPEG. But the compressed data cannot be directly used for image signal processing tasks, which means the decompression needs to be applied before any any operations can be performed. So instead, here we want to consider image processing in the compressed domain. So compressed domain image processing is not really a new thing. In the past few years, people have studied vision tasks in the compressed domain. Like a vision task network takes the latent features as input and directly output the results in the pixel domain, such as a segmentation map or maybe classification results. And last year, we developed this compressed domain ISP that moved the single frame image processing into the compressed domain. And it can achieve common ISP tasks such as denoising and demosaicing. And in this work, we want to combine compressed domain processing with the multi-frame processing. Multiple raw frames will be individually encoded into the compressed domain, and we analyze a line and then merge these frames into a single frame in the compressed domain. Then followed by any single frame image processing tasks. Then the decoder will output the merged single frame. So to achieve this, we have a few considerations when we design the compressed domain. So first, the compressed domain should be naturally suitable for image processing tasks. Right. Second, similar to a regular ISP pipeline, the input to the compression algorithm should be raw frames, and the decompression algorithm should output the RGB image. Third, in multi-frame processing, we need to warp images to match our target frame, so that the compressed domain should be warpable, and it should not introduce any artifacts in the decompressed output. And then to enable HDR imaging, the compressed domain should have the capability to process images with extended dynamic range. And the last feature is what we call progressive encoding. So some image processing tasks may not need the entire full resolution image. So in such cases, we want to use only partial data for the image processing. Considering all these features, we proposed the compressed domain defined by an encoder, decoder, and a vector quantization module. So the UNet type of encoder decoder learns the multi-scale features from the input frame, and the vector quantization maps the three-dimensional continuous feature into two-dimensional discrete embeddings to achieve compression. So one advantage of this compression scheme is that we can compress features with various speed depth based on their importance. So the bottleneck features with lower spatial dimension are quantized with less bits, which means more compression. And features with higher spatial dimensions and maybe more detailed information are quantized with more bits. So this table gives a summary of the network dimension and the codebook size. And here we assume the 512 by 512 raw input. So we can see that the three-dimensional features are represented with a two-dimensional index map. And the codebook for each level has a different number of vectors. So with this setup, we achieve 3.3 times compression compared to the input raw frame, or 10 times compression if compared with the corresponding RGB image. And also here we didn't consider entropy coding, which may further increase the compression ratio. So earlier, I mentioned that the compressed domain should be warpable, and warping should not introduce artifacts in the final output. So during the development, we found that warping in the latent features can actually result in significant structural artifacts in output. So in order to resolve that, we added random warping during the training, which is this blue dashed arrow. So the random warping is applied to the features in the compressed domain, and the same warping is also applied to the label image, so that this will increase the warpability of the compressed space. And to achieve progressive encoding, we downsampled the ground truth image and let the network learn to produce low resolution image using only part of the compressed data. So this should drive the features close to the bottleneck to contain more low frequency structure information of the image, and the features with larger spatial dimension contain more high frequency details. So during the MFPP processing, dequantization or vector lookup is required. So one question is, will this end up increasing the memory requirement again? So the benefit of such a compression scheme is better illustrated with the system memory analysis. So traditional image processing stores the full frame in the DRAM, and the full frame is used by the processing unit. So in our proposed method, only the bit stream is stored in the DRAM. And we also adopt tile-based processing, so that only a small set of coefficients are dequantized for ISP tasks. This will not increase the peak system memory. So after we define the compressed domain, next we want to achieve multi-frame processing functions in this domain. Typically, MFP functions include demosaicing, denoising, registration, deghosting, and HDR blending. So as mentioned before, the demosaicing is actually implicitly achieved with the encoder-decoder. And similarly, we can achieve denoising within this encoder-decoder by adding noise to the training data. But in MFP, image denoising can also be achieved by averaging multiple frames, and then we can do the same thing in the compressed domain. So here we show the results of averaging 2 or 4 noise frames in the compressed domain. And we can observe the reduced noise or artifacts in this text area. So one key function in multi-frame processing is registration. It's because of the camera motion, especially for handheld captures. The frames need to be aligned first before they can be blended. So in a normal camera ISP, this can be achieved with image registration and warping using homography or other warping methods. So in the compressed domain, we can do the same. Here, I visualize one of the feature maps from the feature space, and we can see that the feature map actually resembles a low-resolution grayscale image. So we can estimate the warping matrix from this feature map. And then the estimated warping matrix should be scaled to match the spatial dimension of the multi-scale features and applied to warp the features. So here's the result. We show that registration and warping in the compressed domain will produce the correct registration in the corresponding pixel domain. One thing I mentioned earlier is that warping in the compressed domain may result in artifacts in the pixel domain. And here's an example. So this frame was warped in the compressed domain. And if the model is trained without adding the warping augmentation, the output on the left shows a lot of artifacts. And we avoid this kind of artifacts with this training augmentation. Next, we look at deghosting. So after frames are registered, we still need to decide how to merge the frame. The pixels that do not match across frames should not be blended. This may happen because there's scene dynamics. So here we choose to use a learning-based method to estimate the deghosting map. So as mentioned before, features with higher spatial dimension should contain more information about details. So here we only use the first three features to estimate the deghosting map. And similar to the image registration, the map should be the map should be scaled and applied to all the features. And then here's another example. So we can check the zoomed in region, and it shows that the proposed method can detect both large motion and some small scene dynamics in the compressed domain. The last thing we want to address is HDR blending. So we need to detect the saturated region of the normal exposure frame and replace it with the information from the short frame. So similar to registration, we can also take the advantage of the observation that some feature maps resemble low resolution image. And by using a threshold, we can obtain a saturation map. And similarly, we can scale this saturation map and blend the features accordingly. And then here's an example. So we can see that the estimated saturation map can accurately find the saturated region even in the foliage area. So the full MFP pipeline is summarized here. Here, in this case, so we consider the HDR imaging with 2 raw frames, 1 normal exposure frame and 1 short exposure frame. So after the features of the 2 frames are computed by the encoder, The features from the short frame are first registered to the reference normal exposure frame, and then the saturation map and deghosting blending map are estimated from these features and used to blend those frames. And in the end, the decoder will output the final blended output. So in summary, we have two main contributions. We have proposed a compressed domain defined with an encoder decoder and a vector quantization module. We developed this to tackle the challenges posed by high memory consumption from multi-frame processing. And this proposed compressed domain achieved 3.3 times compression with respect to the input raw frame. And in this compressed domain, we presented multi-frame processing functions, including demosaicing, denoising, registration, deghosting, and HDR blending. And we hope this will pave the way for high-resolution multi-frame processing on mobile devices. And that concludes my presentation. Thank you.
Thanks a lot for the presentation. Any questions? And yeah, by the way, I really liked your paper because this task, well, it's not really addressed that well in research, but this is a problem that you'll be facing once you start working with recent cameras, high-resolution cameras, and therefore I think your work is among a very few ones that is actually presenting some solutions to the problem. And yeah, this is a really important problem, really important task.
Thank you.
By the way, are you also planning to deploy this solution on mobile devices?
I'm sorry, come again?
Are you planning to deploy and optimize this solution just for mobile devices, maybe for ISP or for NPU blocks?
So currently we only have PC simulation, but just to see if this idea is feasible. And technically, there are also parts that's not addressed, like tone mapping. Currently, we don't have tone mapping because that's nonlinear operation. We haven't addressed that, and think we'll consider that, and then we will start to think about the on-device implementation.
Yeah, because here on-device implementation would also be one of the most interesting parts because when I saw your paper, I was thinking about how to make sure that this actually runs on NPU and that or like on ISP blocks, and how to ensure the proper interaction between different blocks. Yeah. That's also a very interesting engineering task. So if you just at some point are able to save to solve this problem, then we expect a paper from you describing how you've done that, because that's really interesting how to do this in practice.
Okay.
Okay, thanks a lot. We don't have any questions, and this means that we have finally time for a break. The duration of the break would be 35 minutes. So we'll start at 12:05 a.m. Well, I will actually continue the workshop. So, and for now we have like 35 minutes, a little bit more to have a break, to have to eat something, to have a lunch, and yeah, see you all in 35 minutes. Okay, so I guess it's now time to resume the workshop. Guys in room 103, can you hear me now?
Yeah, okay. All good here.
Okay, great. So we'll continue, and we continue with the presentation of the third challenge of the with sRGB image enhancement challenge. Again, this task is also familiar for everyone. So we have low quality photos that exhibit various artifacts, and we want to enhance them. And we can find lots of artifacts even on recent smartphones, especially when the lighting conditions are not perfect, and the situation is even much worse when we are working either with very low-end cameras, or many IoT cameras, or we're looking with photos obtained from devices that are rarely old. And this is also one of the use cases, because I'm pretty sure that each of you have your own photo album with photos that were taken more than 10 years or 15 years ago using some ancient phones, ancient smartphones, and the quality of this photo is clearly not okay. And we would also be really happy about improving the quality and removing the artifacts, making these photos looking more lovely. So yeah, the task is clear, and in this competition, the goal of the challenge was to design a solution that can do this on smartphone GPUs and to enhance low quality photos, and be able to do this while processing HD resolution photos. We use here also our common deeper dataset. The dataset consists of photos captured in the wild using several devices. In this particular case, we used photos captured with iPhone and paired photos captured with Canon 70D DSLR camera. Why we're using iPhone? Because the quality of the photos obtained from iPhone is really bad. So the photos look really terrible. And this creates much more opportunities for photo enhancement. So the task itself is quite complicated, and it's not enough just to use some very shallow, tiny architectures here. So you cannot just use sRCNN and get good results. Here you should really design some clever architectures, clever solutions, so that you're able to improve various aspects and bridge the gap between the domain of photos captured with iPhone 3GS and the domain of photos captured with DSLR camera. And all in all, this challenge, you have over 160,000 paired crops, so this is more than enough for training almost any model. As in the previous challenge, as in non-smartphone ISP challenge, here the quality of the solutions was measured using 3 standard metrics, using PSNR SSAM scores, and using mean opinion scores. And again, here mean opinion scores are really essential, as PSNR and the SSAM scores, they do not always reflect the real image quality. So sometimes the scores can be very high, but the photos exhibit various kinds of artifacts, and vice versa. Sometimes the scores are low, but the images are looking magnificent, especially if the guys are using GANs for image enhancement, or just using more efficient, more powerful models that are introducing too many details and generating too many details. The runtime as this competition was measured on the same Adreno 830 and Immortalis G825 mobile GPUs that are found in recent flagship SoCs from Qualcomm and MediaTek, and the models for processing Full HD resolution images. As before, the participants were able to check the runtime of the models locally on their own smartphones using a benchmark application. And here you can see the results obtained in this challenge. Also, it should be noted that many models were very efficient. So you can see that we have 4 solutions which runtime is less than 30 milliseconds. And yeah, this is despite the fact that all the solutions are processing quite large photos. It's not like some tiny patches or some tiny crops. No, these are basically the same photos as you can see on your mobile screen. And also the resolution is close to the resolution of old photos that were taken by 2-megapixel cameras. So in this particular case, what can we see? You can see that we have a challenge winner, a clear winner, that is the ORIG team. And with the solution, it's actually very peculiar because the model proposed by this team is larger than all other models altogether. If you look at the size, it's 12 megabytes, and all other models are smaller. Despite this, despite that, you can see that the runtime on Adreno and ARM GPUs was just terrific. And this again suggests, again, we have mentioned this a few times during this workshop and mentioned before, that the size of the model, the number of parameters that the model has, it's not really proportional to the runtime of the model that you get. The model can be actually quite large, and as we see here, like 12 megabytes, it's just, you can assume the number of parameters that the model has. And this model, for instance, is much larger than the model developed by pixel alchemists. So, like, we have almost, how many? 100 times difference between the size of the models and between the number of parameters. And as you can see by looking at the runtime, that, yeah, it doesn't really matter, because despite the fact that this model is 100 times larger, 100 times larger than the model proposed by the third team, its runtime is around like 6-7 times faster. So, and again, this suggests that it's not only the number of layers, not only the number of parameters that your model has, it's all about the design that is that can run efficiently on the target accelerator. And yeah, the challenge winner actually demonstrated really nice results. So the solution is very performant, you get very good PSNR score, you get the best mean opinion score. So the solution was also demonstrating the best visual results. And it demonstrates less than 15 milliseconds runtime on Adreno GPU and less than 35 milliseconds runtime on ARM GPU. So yeah, because of this, it's really about optimizing and adjusting the architecture, tailoring the architecture to some target hardware. And now let's look at the results proposed by the first two teams. So challenge winner, 12 megabyte model. You can actually feel the size of this model just by looking at this diagram. So the team proposed parallel linear unit architecture that has an encoder-decoder structure. It has a couple of very interesting blocks. So for instance, it has parallel convolutional branches here combined via element-wise multiplication. So you have two parallel branches, and to go further, you need to perform element-wise multiplication of the outputs of these branches. Also, you have global feature extraction module here, and the guys explicitly even mentioned in the paper that it's done to deduce elimination prior, and this is the same stuff as I described here during the presentation of the Learn Smartphone ISP paper, that in order to adjust brightness, in order to work with white balancing, we really need blocks that are performing global feature extraction and that can alter all layers. Yeah, and the model was trained with a combination of L2, MSSM, and perceptual losses. So in this case, again, it's not enough just to use L2 loss. If you want to get good visual results, you need to also take care of perceptual losses, either in form of GANs or in the form of VGG-based loss or any other form. But that is really important. So this is the team. You can find a more detailed description of the solution and a more detailed description of the training strategy in the paper. And yeah, the second solution proposed by team ZX Flip, it's more traditional architecture, just a pure unit-based structure. It has plain unit-based structure. And yeah, the idea behind this architecture is also very clear, just to optimize the number of convolutions that is done at large scale resolution. So we are moving all computations to lower scales, and therefore we are making the inference more efficient. This model was additionally trained on an extra blind image enhancement dataset, and the whole model was trained with a combination of L1, PGG-based, and GAN losses. This was also part of the reason why the model was showing quite nice visual results. So again, you need to use either perceptual or GAN losses in general if you want to get not only good PSNR scores but also good visual results. The paper describing all solutions is also available online. You can download it by following this QR code, and you can find a description of all developed models and all the evaluations there. And I guess if we don't have any questions, so do we have some questions? Okay, we don't have any further questions, so we move to the next paper presentation, which is called Beta Parameter Efficient Task Adaptation for Hybrid Transformers, that is given by Syed Shahir Sarwar. I'm very bad at pronouncing the name, so sorry. I think it's not only you, it's like lots of guys. I'm really bad. And you're from Matching, right?
Yeah, I'm from Meta. Yeah.
So yeah, one moment. Okay, I will make you co-host. Yeah. So you can now start sharing the slides.
Yeah, just one sec. Yeah, sorry, I need to reconnect because of
yes, sure, no problem.
Yeah, so
yeah, in the meantime, if you have any questions, you can ask now. We have 1 minute break and 1 minute time for asking us, and if you have. Welcome back. You're muted. You're muted. You need to unmute yourself.
yeah, can you hear me?
Okay. Yes, we can hear and we can see.
Okay, great. Okay, so I'm Syed from Meta Reality Labs Research. I'll be presenting our paper PETA, Parameter Efficient Task Adaptation for Hybrid Transformers. Okay, so first I'll talk a bit about the motivation for this work. So we know the explosive boost from the transformer-based LLMs in the AI field, and the model sizes are keep on increasing almost exponentially. And we see similar trend is coming to computer vision domain as well, with VITs as foundation models. And then we also see the popularity of the VLM architectures due to the Gen AI approaches. So all these today mostly developed in servers, server kind of infrastructures. and it becomes very difficult to support these interesting and very useful features on edge devices. So that is the main motivation for our work, that how we can make these models more efficient for different tasks and be able to deploy on resource constrained edge devices. Okay. So before I go to details, just want to mention the collaborators for this work. So Maximilian Augustine is the main author of this work, who is now in Mistral AI. He was a former intern in our group. And then the other collaborators are Mustafa El-Hoshi, Yuchen Li, Sai Jian Zhang, and Barbara De Salvo. So for this work, I'll first briefly explain the framework we developed, and then I'll explain the experiments and the results. So we first investigated different architectures for CV tasks in resource-constrained devices. We explored CNN architectures, transformer architectures, and hybrid transformers. And we have found that hybrid transformers are most efficient in limited memory and compute based systems. So we use hybrid transformers as focus of our research, and for efficiently adapting for different tasks, we use a hybrid transformer backbone. As you see here as an example, we are using efficient former as a backbone. And then we add the separate heads for different tasks for adaptation. The backbone is usually frozen for task adaptation. And in hybrid transformers, usually we have some blocks with convolution based operations and some blocks with transformer based operations or attention layers. So in our work, we use the inspiration from LLMs, the use of LoRa, low rank adapters. So we use that technique to both of these blocks, the convolution blocks and attention layer blocks. And that allows us to achieve very good performance on task adaptation, both in accuracy and performance. So I'll next describe some of the experiments. And before going into details of the experiments, I'll mention the baselines we have used here in this work. So we use efficient former L3 and L7 as the hybrid transformer backbones. And then we use VIT big and VIT small as pure transformer-based backbones. And here, most of the cases will compare efficient former L7 with VIT-B and efficient former L3 with VIT-S, because they are in similar range of size and number of flops. However, you can see that because of the hybrid nature of the architecture, both of the efficient formers are highly fast compared to the VIT architectures. And the reason is mostly the convolution operations are very efficient on NPU architectures or NPU accelerators versus the attention layers or linear layer operations. Okay. So first, we'll use the efficient form L7 as our experiment setup, and we'll go through the different techniques we applied here. And then in the next slides, we'll go to more thorough analysis. So for task adaptation, what we do is we use a pre-trained backbone and then attach some heads for different tasks. And here, if we don't retrain anything, so on the right column, we see how many parameters we are adding or retraining. So if we don't retrain anything, we get some accuracy for those new tasks. It's kind of zero-shot learning. But then previous works also demonstrated LoRa being applied to transformer blocks. So here we add LoRa adapter of rank 8 in the attention models, and that requires training of these many parameters, and we see there's a increase in accuracy. We can increase the rank of the adapters. That increases the accuracy a bit more, but it also increases the training parameters. Then we added adapters in the final MLP layers, which increase the accuracy slightly, but overall the number of trainable parameters also increase. On the other hand, in our work, we use LoRa adapters for convolution operation, which have not been done before. And here we use only rank 1 and rank 2 as two variations, and we see we can get significantly improved mean accuracy for these different tasks with still a reasonable number of trainable parameters. Next, we compared this performance of efficient former on different fine-grained classification with the pure transformer-based approach with VITs. And we see that the mean accuracy in both cases, like efficient former L7 and L3, beats the both VITs. And overall, the trainable parameters are in the similar range. Just to zoom into the difference between the two approaches, on the left side, we see how many new parameters we are training for our approach. And here you can see that our approach, Peta 1 and Peta 2, the additional parameter training is very minimal, whereas the accuracy is the highest, versus the traditional approach of LoRa and attention model fine-tuning or full fine-tuning requires orders of magnitude higher trainable parameters still don't reach the high accuracy. And on the right side, we see the comparison between VIT and efficient former approach. Even though we see that the number of new training parameters are almost similar, but the number of flops for efficient former are much lower than VIT approach, while the accuracy is still higher. Then we also consider different domain-based tasks. Previous ones were only classification tasks. Here we are doing object detection and instance segmentation. And we see that Peter beats all other fine-tuning approaches or LoRa approaches. Only the full fine-tuning, which is the most inefficient approach, is on par or slightly better than our approach. And the last one we did is we tried to also improve the efficiency of the backbone itself by compressing the backbone with pruning or sparsity. We see that even with up to 90% sparsity for both efficient form and VIT, the accuracy on ImageNet 21K is still very close to the baseline, only 3% drop. On the other hand, the number of parameters is almost 10x reduced. So our future work is to apply this sparse backbone to the task adaptation to see how that impacts the overall task adaptation performance. And can we eventually use this efficient backbone together with the LoRa adapters or not? So in summary, our contribution is development of a framework for parameter efficient task adaptation for hybrid transformers, which has not been done before. We demonstrate performance gains using these hybrid transformers with LoRa in accuracy and speed up. we demonstrate the utility in different domain tasks, like not only classification, but also object recognition and instance segmentation. And finally, we apply compression techniques to improve the parameter efficiency further by compressing the backbones of these adaptation models. So that's all from me. If you have any question, I'll try my best to answer those. Yeah, thank you.
Yeah, thanks a lot for the talk. If anyone has any questions, you can again ask them. But again, it's kind of difficult to do this in the current setup because the guys who are watching us in place at CVPR, it's a little bit tricky to ask questions there. Okay, great. Again, thank you for the talk. If we don't have any questions, then we are moving to the next presentation, which is NAS, generating efficient yellow models using activation NAS. The talk will be given by Sudhar Shah from DeepLight.
Can you hear me?
Yes, we can hear you, and you can now start showing the slides.
Okay. Yeah, so thank you so much. I'll just check if I can share my screen or not. Can you see my screen?
Not yet. Ah, okay, now we can see.
Okay, so yeah, thank you so much for giving me opportunity to present this paper. My name is Sudhakar Shah. So my co-authors are Ravish Kumar, Darshan Ganji, and Ehsan Saburi. So we actually come from DeepLight. It was a startup a month ago. We got recently acquired by ST Microelectronics, so our affiliation is changed, but in the paper it's still same. So the paper title is generating efficient YOLO models using activation NAS. The concept is very simple, but the results are very encouraging. So that's why we thought about writing this paper. So the motivation is what we have seen in most of the models, whatever we see in object detection or classification or pose estimation, primarily computer vision models. Invariably, all the models in literature use a single activation function, which means either it's ReLU or CLU or hard switch. So throughout the model, it's same activation. If you look at the graph, it's clear that for YOLO v5n, if you run on any recent NPU, then the CLU models are slowest, but most accurate. The ReLU models are fastest, but less accurate. And the similar trend we see in other models, and this is very consistent in all models. So the motivation of this work is if ReLU is fast, if CLU is slow, and accuracy relationship is inverse, can we actually try to create a mixed activation models, which means every layer will have a different activation. With that motivation, we started working on this concept, and we call it activation NAS because this is a network architecture search method which just targets activation functions. Now the contribution is we are using NAS, which is a bit different than traditional NAS. So traditional NAS actually uses invariably uses fine tuning or training of the model, which is very expensive. It's prohibitive for large data set and models, and very slow. So what we are doing here is we are using a different concept, and we are using zero cost proxies to estimate the accuracy. So we'll see the details how exactly we do that. So that shortens the optimization time. Another important aspect is that the graph which I showed here is going to be different for different hardware, which means the ReLU versus CLU performance difference may not be that prominent on GPUs. It may be prominent on some CPUs. It may not be prominent on some NPUs. So that's why it's very important to see to use hardware in the loop in this NAS process, and this is the most important thing because unless we know the real impact of every layer and every activation on your optimization, we cannot really design a optimized model. So the concept is this. So for example, we have the first ReLU activation here. Or basically originally it was CLU. So we replace that with ReLU, just one activation at a time. And then create this as a candidate model. And the same thing we do second time, we again replace the second ReLU. So this is second candidate model for second layer, then third candidate layer model for third layer. At the same time, right now, I'm talking about just replacing CLU with ReLU, but there may be multiple candidates. So it can be ReLU, it can be hard switch, it can be ReLU 6, leaky ReLU, which means we can have 5-6 different proposals for every activation, every layer, every activation, which means if you have 50 layers, then 50 into 5, 250 models, which we are talking about. And in detail, how does it work is this block diagram shows this clearly. So we start with the model, and the layer selection function gets one layer at a time. So let's start with first layer. Activation replacement takes different activations from the library, replaces one layer at a time, as I mentioned, and then creates the model. Then we use something called zero cost estimator to estimate the deviation of score from the reference model. So this zero cost estimator doesn't give you the real accuracy, but it will give you a relative difference in accuracy, potentially accuracy. And the same thing we do with latency computation. So we export this model with one change at a time. And let's say we are talking about an NPU. So we do the inference on NPU, and we collect the latency number for the same model proposal. Now, how does it look like in terms of the table is this. So layer 0, layer 1, layer 2. So layer 0, proposal number 1, proposal number 2. So this will give us a table which we call as accuracy table. And the value here is reference accuracy minus the proposal accuracy. So every delta value in this table shows how much impact on accuracy did the change in activation for that layer made. So that's why we call it as micro NAS. And we do both from latency and accuracy measurement perspective. So this is how we generate these tables. Now coming back to the accuracy estimation. So we use something called zero cost proxies, which is used invariably in research field for training free NAS. And we are trying to use newer methods for zero cost proxy, and we also did a detailed analysis of which proxy works better. So usually we try to use expressivity, which is basically to see how uniformly the features are distributed across the orientation in the feature space, which is called isotropy. If the isotropy is strong in feature space, which means the features are less correlated to each other, which means the model has more capacity to learn. So this gives you the reference of first model versus second model. It doesn't give you the actual accuracy. The progressivity does the same, does it in a different way. It checks the feature space progressivity along the depth of primary blocks. And we have a couple of other zero cost proxies. We are not going into detail for that, but the main point is we did a very thorough analysis of these proxies on one of the benchmark which we have. So it is called the MCU bench. So these are around 350 YOLO-based object detection models. So you can see that some of these proxies are very good approximation for accuracy. So that's why we chose one of that to use in our work. And this graph shows the upper one is actually shows the cost, and the lower one shows the MAP for all those 350 models. So you can see a very good correlation for each model. So that's why we were able to use this for this work. Now, once we have these two tables available, we do something called the architecture search. So what we do in architecture search is the objective here is to minimize the delta latency and find the best possible combination for each layer based on the delta latency. And we can put a constraint of what is the minimum accuracy drop we want. If you want 0, then it will try to find a model with minimum latency with 0 accuracy drop when we make these changes in the model. We can also do it in a different way. We can have objective as accuracies, like maximum accuracy, and we can have latency maximum as a constraint. So using these two approaches, we can find model proposals. Once we have model proposals, we can fine tune that model, and that will become our optimized model. Now, just to give the final results, you can see in this orange and yellow, I have shown the MAP of YOLO V5 if you use CILU activation throughout, which is the standard YOLO model, 33.66, and the latency on NPU1 is 22.35. And RAM, which is very important on NPUs. This is not usually considered very important for many applications, but on NPUs, MCUs, it's very important. So 1230 kilobyte. And ReLU is 588. So you can see the difference. This makes a lot of difference generally. So people directly use this if they want to have optimized models. So we tried many different options, but the last two are the ones which we get from activation NAS. So you can see this accuracy is very close to the reference accuracy, which is CILU model, and much better than ReLU. But the latency is almost similar to ReLU, which means this model is more efficient with better accuracy compared to ReLU. In terms of RAM, you can see that this particular model actually has even lower RAM consumption compared to the standard ReLU model. So we did detailed analysis on different hardware. In some hardware, we found this to be useful, some hardware not useful, because the reason is some hardware can process both activations, all activations in similar way efficiently. Some hardware cannot. So for example, in case of A53 CPUs also, we could find a better model compared to the reference model with very little drop in accuracy. We also tried this with YOLO V8 models, and all these are trained on Coco. So you can see that the reference model has 190 millisecond accuracy, and we can get model at 114 millisecond with actually almost same accuracy. There is some improvement, but I think that's just minor. It's not an improvement. Same with other NPUs also, we found this improvement. So yeah, that should be all for the presentation. If you have any questions, then I'm open to answer now.
Thank you. So any questions? And here I have a question. Which NPUs did you use? What, like NPU1, NPU2, NPU3? What?
Okay. So yes. So basically, I got this feedback when I got the feedback for the paper. So the reason why we have not mentioned this, because one of the NPU was from our company, which was not released, but now it is released. So this is N6 from ST Microelectronics. So the first one is in this one. Sorry, yeah. This NPU is N6, and NPU3 is also released from the company. It's called STM32 MP2. So this is the one. And the third one is from some other company which is not released, so that's why we could not name it. But by the time we sent this paper, it was not released. It was released very late.
Yeah, because it's also good to understand what is the exact hardware. And the NPUs, they are used in which products?
Can you come again?
The NPUs, in which products are they used? So this the target of the NPUs are IoT or?
This M6 was released very recently. So the it's actually a very low cost NPU below $5. So it is also targeted to be used in automotive. Some of the automotive use case, not the safety critical ones, and of course in surveillance and many other applications, because it has a very low memory footprint, and that's the reason we are talking about such a low RAM. Like usually,
yes,
you don't go beyond a couple of megabyte RAM.
And this NPU, it should be integrated into some chipset as well, right?
Yes. Yes.
So, okay, yeah, interesting.
Yeah.
Because this is also quite good, example.
Yeah, and just to extend this, we are actually doing this for all other optimizations, because this micro NAS can be used for all different optimization methods. But this was very particularly useful for models which uses activation functions, and I think all the models use.
Yeah, and this is actually also a very good example of specific optimization for specific platforms. So like you have your original model, you have original task, and sometimes it's not just enough to play with the layers and play with like different options, different activations, or different operators that you have. Sometimes you need to be more creative, and here like it's just a really great example when you from one side use a NAS, from other side you have a good idea, and finally you come up with quite nice solution that is targeted for specific NPU. So like we hope that that the participants of our challenges will watch your talk, and we'll also try to do some similar stuff during the development of their models.
Okay, yeah, thank you so much.
Okay, thanks a lot. And now we are moving to the next presentation, which is S2A. No, it's it's Flare SVD, fast and latency aware singular value decomposition for model compression. And the talk would be given by Moritz Thoma, and he's here. I made you a copy so we can start sharing your slides.
Okay, am I audible online?
Yes, we can hear you.
Great. Yeah, thank you very much for the opportunity to present this work here today. I'll be discussing our work Flare SVD, which means fast and latency aware singular value decomposition for model compression. Special thanks goes out to the entire team that is also listed here on the presentation slides, who made this work possible in the first place, and always help push the boundary for our projects. Oops, not this one. Okay, so let's get right to it. You are all here because of the same problems. Basically, models are too big to run on smallish kind of hardware, and you always need to do some kind of compression to make it work. One very prominent compression, or increasingly more prominent compression, is singular value decomposition. The cool thing about it is that it maintains the internal structure of the model in terms of activation shapes. So it is applicable, relatively non-intrusive, different to something like structure pruning, where the changes to the model are much more difficult to make. As you can see here, it can reduce
the size of the weights, so it can have fewer parameters, and as a consequence of it, also fewer flops by reducing this rank dimension with the decomposed versions here. For this work, we had two main questions that we want to investigate. First one is, can we improve the decomposition part of it to have more representative components for these smaller variants here, or for the smaller representation? And the second one is, which rank should we choose to reduce the parameters the best way possible? So for that, of course, a lot of other people have spent thought on this already. So I have brought some of the related works here. And for improving the SVD component, there are two bodies of work. The first one is here on the left side. They use sparse matrices or additional parameters in another way to try to reduce the compression error that is introduced with the SVD. But of course, introducing more parameters always comes at the cost of more runtime. So we didn't thought those were the best ones really, but the concept 2 here on the right, which you can see also has some very recent papers, especially with SVD LLM, introduce no overhead at runtime because they calculate the scaling in the beginning once. So this is actually the kind we want to proceed. The special thing about SVD LLM, as the name suggests, it's built for LLMs. So the first question there was, how does it work on vision models, which was the main focus on our investigation. So yeah, that is one of the remaining points for related work there. But let's have a look at the other question next. So in particular, what rank should we choose? So there are many to choose from when you have 768 in case of width. Even if you divide it by 8, you still have a lot of different combinations that are possible. So how do you choose? So a couple recent works like PELA, which was presented at CVPR last year, or SVD LLM also could just go with uniform rank, which of course is the easiest. But there are also more advanced approaches like Comcat, who use gradient-based rank selection, ASVD, who do sensitivity-based rank selection, and FastLRD, who do a greedy search. You can see that they are different in terms of effectiveness and speed. Of course, uniform rank search is very fast because you don't need to do any search at all. The gradient-based search is very, very slow, and ASVD is pretty fast still, but its effectiveness is not the best. And FastLRD, yeah, is not so fast anymore, but pretty effective. Yeah, but still you can see that there is a pretty strict trade-off between performance and the effectiveness, and we believe that there's a better way of doing this. In particular, what we find are the main challenges of the related work that are not solved that greatly is the activation-aware SVD. So you can see here we tested the similarity on a DIT model with less number of calibration samples with the SVD LLM approach, or Cholesky SVD is what they are doing. And you can see that the similarity degrades relatively quickly with fewer samples. Second is the speed effectiveness trade-off that comes with the search is not using very effective criteria to quickly iterate the search space, and therefore either limits it to go through it quicker or it takes very long to search it. And the third one, as you have seen in the previous one, nobody really considers latency in their choices. Everybody just tries to decompose as much as they can without considering hardware properties. But as you can see in this plot here, even if you compress some layers, there is no latency benefit at all, or it's even slower if the rank choice is relatively big, because the multiple fetches from memory are slower than just processing the thing in one go. And also here, when it comes to very small layers, the break-even point until there's any effect at all is very low because the computational unit was not 100% utilized to begin with. So there's really no benefit to be had there. Okay, so realizing these three things, our method has three key components. So the first is we introduce Leadoid-Wolf shrinkage into our decomposition
to stabilize the variances, and that really helps with the similarity with fewer data, as you will see in a second. For the second part, we introduce a binary search algorithm that takes advantage of this monotonous behavior of Cholesky decomposition and very rapidly is able to search for choices for the individual layers. And finally, we use a latency predictor for each of the layers to make a choice. Okay, should we use decomposed weights here or not? And these three components together make up the FLAR SVD algorithm that we used for the subsequent experiments. So let's jump to evaluation here. So starting with the Leadoid-Wolf shrinkage effect on the similarity in the first layer, you can see that when we use the different samples again here, and we add the shrinkage, the stability improves a lot, and we get much higher similarity after reconstruction with the Leadoid-Wolf shrinkage applied to it. So we can see that the shrinkage really stabilized results, especially for fewer data, which was a really nice finding, and made us use it subsequently for the rest of the experiments as well. So next up is the improved rank search speed, or the speed effectiveness trade-offs. So let's look into the key results here. So this is a little bit of a longer table, so let's take a little bit of time to explain it. So we have a bunch of approaches. A few of them you would recognize from the related work again, or all of them you should recognize from the related work. These are basically the most recent advanced approaches that exist, or the most effective, or both. So for this table, to gather a large body of results, we did it on a V100 and measured from left to right the number of parameters, the number of flops, the number of, or the top one accuracy, and the latency on ImageNet data on this card using TensorRT. And as you can see, we used three different models: conf model, DIT model, and Mamba Vision model to represent the most common architectures that are used in the space. And as you can see, we very consistently have the best latency here and the best accuracy also, with the exception of this Tomcat result here, which has really good latency, but not so great accuracy. And this is because they do a little trick with the decomposition of multi-head attention that makes it significantly more efficient by dropping a lot of parameters, but you need a lot of time to recover after this adjustment. Which is why without retraining here, it is a lot less accurate. Yeah, but you can see also the latency predictor at work. Actually, for example, here we have significantly more parameters compared to the other works, a little bit less flops, but you can also see it in different places here, that even though we don't have so different stats to the other ones, still the latency is a lot lower, because it takes into consideration, okay, decomposing lowers theoretical flops, yes, lowers parameters, also yes, but it will not do us anything in latency, so we might as well keep the original weight. So even with more parameters, we can have lower latency, or at least a lot more accuracy. Yeah, so you can see that already the accuracy latency trade-off is significantly improved compared to other works. So how does it look on edge targets now? So we have the same setup again, basically, but this time for Jets and Orin. And you can see the same approaches again. And especially for floating point 16 here, the gap is really large, because kernel optimization for, or what we assume is kernel optimization and algorithm selection for Jets and Orin is not working that great on decomposed matrices. So it is really crucial not to decompose bad ones, which resulted in this good latency for our one sitting below the baseline, while everybody else was exceeding the baseline accuracy by a lot, highlighting the importance to actually check if your model has better latency with the decomposed weights or not. But we can see overall the same trend repeating again.
with the accuracy being a lot better and the latency being lower also on edge targets here. So finally, speed is pretty important. So we looked at the speed of the different rank search algorithms that I introduced earlier in the related work. And you can see here that our algorithm has very similar time in terms of, or compared to ASVD, and a lot less time compared to Comcat. And within that time, our algorithm actually finds a lot better results when it comes to accuracy and then also latency. Again, Comcat uses this trick, which makes it a lot more efficient. Fast LRD does some fine-tuning in their search already, which makes it take a lot longer. Also, they don't publish code, so it was hard to reproduce the algorithm, so we just used the values from their paper. But even though they used a faster GPU than we did for their search, still with one epoch of fine-tuning of our algorithm, we still have fewer time and better results. So the trade-off when it comes to speed, accuracy, and latency is really great with our algorithm. Okay, so this was the second part of our question. So now we have gone over the entire method. So it's time to draw the conclusions. So on the right-hand side, again, you can see the entire algorithm, and it has these three key components. So we improve the SVD stability by introducing the Slidoid-Wolff shrinkage that stabilizes the whitening. We have this binary rank search that makes use of the monotonic property of the decomposition. And we introduce the latency estimations into the rank search, which helps choose or eliminate bad ranks and only make effective choices when it comes to selecting ranks. As you have seen, that works pretty well on a wide range of models and on both edge targets and server hardware. For future work, what we would like to explore is multimodal models. So when the model becomes more complex, multiple inputs, potentially also multiple outputs, does it still work? Can we apply this? And right now we use a layer-based latency estimation, so not consider the end-to-end latency, but actually only the layer-based latency, which works pretty well, as you can see. But another direction to look into would to view end-to-end latency of the model and incorporate that feedback. Yeah, that's all for the presentation today. Thanks a lot for listening, and yeah, I hope I didn't.
Yeah, thank you for the presentation. Yeah, a very good and interesting solution.
I'm happy to take questions. Sorry, I missed that.
Yes, if anyone has questions.
I have one question, if you don't mind.
Yes. Yeah.
Yes. So usually for decomposition, because we actually replace one layer with multiple layers. So for very small devices, what we have seen is there is a latency impact because of the memory fetch. It improves the memory fetch. But for larger devices like small GPUs, etc., we have not seen much improvement. It definitely reduces the size of the model, but from latency point of view, we have not seen that. So do you think that is a true observation for larger, let's say on GPUs? The decomposition will not impact much on latency, but yeah, the size definitely it affects, because on larger GPUs, this RAM fetches are not that expensive. So is that a correct observation?
So we found benefits for a variety of models, also on larger GPUs. But if compute becomes less and less of your limiting factor, of course, the memory fetches become more of a problem. So if your compute is not utilized by the model you run on it, the benefits of it will be very minimal. Is that what you meant? Sorry.
Yeah. Yeah. Thank you so much.
Okay. Yeah. Any other questions? Please.
How many rank did you choose? Like, what were the choices?
So the rank choices the algorithm made, or the selection overall?
Yes, selection overall.
So we
allowed only selection of increments of 8 in the exactly. So for 768, which is the standard VIT dimension, that would be something like, I mean, just under 100 choices.
So yes, something like that.
Yeah. So
And what would the layer you use decomposition?
we used linear layers for the decomposition and decomposed linear layers into 2 smaller layers.
Yes, I mean the architecture was it just query, queue, value, or
all of it? When it was a linear layer, it was considered.
So
you can see it here actually.
did you use to MLP as well?
Yeah, you could. So
I couldn't see.
no. I just like this was one of the backup sites.
Yeah. So and you said for the selection you use binary.
Yes, binary search.
So you iteratively and calculate the accuracy of all the choices and then use binary search, or
no, we used an estimation of the error, or like a single forward pass or 2 forward passes to estimate the error with the given rank choice, and optimized the binary search for a certain error target.
So you have to run forward pass for like 100 of the choices and then use binary search to get the prediction.
No, you select a rank that you want to evaluate, you evaluate it, you check if it's lower or higher than the error that you target. If it's lower, you check the next one in the, and the latency criteria basically helps to speed it up, because it also asks, okay, is this violating the latency threshold? So it predicts, okay, is this faster or slower than the original weight? If it's slower already, it's no point in evaluating, so it moves on directly. So then it can iterate a lot quicker.
And question, like we have to fine tune once you decompose it, the entire architecture, right?
You can, but the values shown, all except the second one in the search, were without fine tuning. Good, thank you. Any other questions? Great, then thank you, and there will be an open source implementation soon, very soon.
Okay, great. Again, thanks for the presentation. And the next talk is S2A, a unified framework for parameter and memory efficient transfer learning. Do we have a presenter? Okay, so again, S2A, a unified framework for parameter and memory efficient transfer learning. If the presenter is here, please unmute yourself. And if the presenter is in the CVPR room, then also tell us that you're here. Okay, so I don't see the presenter, so we move to the next talk, and we have again becoming on time. The next talk is robust 6-DOF pause estimation against depth noise and evaluation on a mobile dataset. And I guess the talk would be given by Kellen Yao, right?
Yes, I will share my screen.
Mm-hmm.
Can I see the screen?
Yes, we can see the screen and we can hear
Cool.
you.
Perfect. So I'll get started. So my name is Colin Yao, and I'm the co-author of the paper Robust 6 Degree of Freedom Post-Estimation Against Depth Noise and a Comprehensive Evaluation on a Mobile Dataset. And this is a work collaborated by UC Berkeley, CMU, and UCLA. And so the key problem we're trying to solve in this paper is to do 6-DOF estimation on the mobile dataset. So before we dive in, I want to provide you some background information. So 6 Degree of Freedom post-estimation is a regression task to estimate an object 3D XYZ coordinates and also the rotation along the 3 axes. It has a wide range of applications in augmented reality and also robotics. And there are actually a lot of work around doing 6 degree of estimation based on RGBD inputs, and they can already achieve very good performance. However, most of them they are testing on the high quality depth sensors like the Azure Kinet and RealSense cameras. So as a merging application on the mobile augmented reality, it is unclear how the 6 degree of freedom models perform on the mobile devices. So the core challenge for a mobile 6 degree of freedom estimation is that the mobile depth sensors, like an iPhone LiDAR sensors, they produce a very low resolution depth map with distortions and with long tail non-Gaussian noise. This will cause the performance of the current SOTA RGBD methods degrade a lot under sensor noise and low quality depth inputs. For example, as you can see the visualization of an iPhone 14 Pro LiDAR 3D point cloud, there are a lot of long tail noise and distortions along the surface of the object. So to solve the challenge we have, we bring 3 key contributions. First, we release a DTDD mobile dataset, which is a new RGBD dataset using iPhone 14 Pro. And we also introduce a DTDD net, which is a transformer-based 6 degree of freedom pulse oximeter with the depth noise robustness. And for the experiment side, we also do a lot of extensive evaluation showing the SOTA performance and noise robustness of our models. And here is a short videos of our paper. And here's some visualization of our data set. And here is how our models eval on the data set we proposed. Yeah, so this is just a brief piece of how our model perform, and let's dive into each of the contributions. And for our DTDD mobile dataset, we collect using the iPhone 14 Pro with the OptiTrack motion capture system for higher accuracy. Basically, we are using the motion capture system to capture the poses of our iPhone 14 Pro in the environment. And then we use Roku markers. We know the location of the Roku markers also in the environment. And we use the Roku markers to calibrate and to ease our data collection process of the object posts. And in dataset, we have around 18 objects within 100 scenes, and each scene will have different occlusions, lightings, and post diversity. And we also have different covers on the table we're collecting. So for our dataset, compared to the Kinet and Intel datasets before, we have more realistic mobile scenarios in this case. For example, in this visualization of our dataset, as you can see here, we have a lot of objects in different conditions and different lighting conditions and with occlusions and different distance. And we also have the bounding box as the ground truth and also the semantic labels. And for the LiDAR depth visualization, actually here you can see there are a lot of depth noise and distortion along the surface as well. So this will be one of the characteristic of our dataset. So we also, along with the dataset, we also introduce a new evaluation matrices, which is the depth ADD. So depth ADD is a matrix to quantify the LiDAR depth distortion, where we measure the average pixel-wise L1 distance between the depth LiDAR and the depth ref. Depth ref is basically we render from the ground truth 3D post of the CAD models. So with higher depth ADD, it means the depth sensors from the iPhone will have more noise and distortions. And we also did an object level analysis on each of the object in our dataset. And here is the box plot of each object. And as you can see, a lot of the object, basically most of the object have a very long tail outliers in that case. And this also demonstrates the no long tail non-Gaussian noise of our dataset. So here comes our DDD net architecture. So the input to our model is the RGB image, the depth map, and also a CAD model. And in the first stage, which is the feature extraction, we extract the RGB and the RGBD depth map using two branches. And in the second stage, we fuse them together in two steps. The first step, we're doing modality fusions. We basically fuse the depth features with the RGB features together. And then we use point-wise fusions where we are focusing on some key points and make sure they're aligned. And output of our model will be the rotation and translation alongside with and confidence of the 60 post. So besides the model architecture, here is the key design choice we made to provide robustness to the noise depth map. So we introduced the chamfer distance loss into the training pipeline to denoise in the 3D point cloud. Basically, we are using the p hat as the point set we are predicting, and p as the reference point set, which is coming from the CAD model ground truth. So we are basically trying to predict it closer with the targeting guidance point. And we also introduced geometry feature filtering, which filter out all the non-Gaussian noise. The way we are doing it is in the feature extraction part in here. When we are dealing with the depth features, we first using a fast Fourier transfer to transfer into frequency domain, and we use in shallow MLP to normalize and filter out all the long tail distributions, and then we use inverse fast Fourier transfer to filter it to make it back to the geometry feature space. And as you can see before in the geometry feature space, the distribution is very like long tail, but after filtering, we can normalize it to a Gaussian distribution. So here are some quantitative results of our DTDD on our DTDD mobile dataset. We evaluate on the ADDD AUS and also the ADDDS AUS, which are the standard matrix for 6 degree of freedom post-estimation. The S here means the symmetric object. So on average, we have the SOTA performance compared to all the other RGBD methods, the dense fusion, megapulse, EX60, and bundle SDF by a large margin. And besides SOTA, our model also show very stable errors, even under a very large depth distortion. As you can see in this image, for the depth ADD, higher value means higher depth noise, and for the y-axis, we are using like ADD as the y-axis, which means the inference error. So our model, the red region, shows that we can have the lowest inference error despite the depth noise. So we also experiment on the performance drop for each baseline while shifting the dataset. So here is the quantitative results on YCB dataset, which is a standard dataset we use for 60 post-estimation. And here's the quantitative results on the YCB. And as you can see, the DTDD-net achieved the highest performance on both the dataset, and it showed less performance drop in iPhone LiDAR sensor noise. And here is some qualitative results of our model. So as you can see, our model can have more robust performance under different lighting conditions and different distance, and also with different coverage of the table. And yeah, that's all of my presentation. Thank you guys for listening, and feel free to ask any questions.
Yeah, thank you for the presentation. Is this data set already available?
Sorry, what's the question?
Is this data set already available?
Yes, the data set is already available on the website.
Okay, great. Okay, do you have any questions? Yeah, the data set is definitely interesting.
Yeah.
And yeah, the proposed solution actually also makes a lot of sense.
Is there any other questions?
Well, looks like we don't have any other questions. So, well, he released the data set. So the guys would first go and check the data set, and I think then they will get all questions after working with it a little bit. So, okay, thank you a lot for the presentation. And now we are moving to the next talk, which is cycle training with semi-supervised domain adaptation for real-time mobile scene detection. And I see the presenter here.
Can you hear me?
Yes, I can hear you. And you can start sharing this screen.
Hello everyone. Thank you for being here. My name is Phong. Today I'm excited to present our paper, Cycle Training with Semi-Supervised Domain Adaptation, Reaching Accuracy and Efficiency for Real-Time Mobile Scene Detection. We all know that deep learning has revolutionized computer vision. Models can now classify images with incredible accuracy. But these powerful models traditional live in data center running on high-performance hardware. But in the real world, we have smartphone, IoT device, and other systems that operate under strict constraint, limited processing power, and very little memory. So this creates a fundamental conflict, which is the core problem our work address. How do we get the best of both? How can we achieve the high accuracy of a large model while ensuring the real-time efficiency needed for the mobile deploy? To solve this, we propose a framework that can be broken down into two main phases. The core idea is to use a large, powerful teacher model to train a small, fast student model. In the phase one, it's about generating better data. We use a technique called semi-supervised domain adaptation. Here, a teacher model help us create high-quality label for the data that previously unlabeled. This expand our dataset and make our training process more robust to real-world variation. Phase 2 is about training smarter. Instead of a simple fine-tuning process, we introduce a new strategy called cycle training. This is a multi-stage process designed to carefully transfer knowledge from the teacher to our lightweight student model, ensuring it learns powerful features without overfitting. So how does semi-supervised domain adaptation work in our framework? It's a straightforward but highly effective process. First, we take a large, powerful pre-trained model and we fine-tune it on our label training data. Next, we use this now expert teacher model to make prediction on unlabeled data. Of course, not all prediction will be correct. So in the crucial third step is prediction. We only keep the one where the model is highly confident in our experiment, above an 80% confidence threshold. This highly quality prediction become our pseudo label. The result is a larger and more diverse and more effective training pool for our student model. Now that we have the in-hand dataset, how do we use it to train our lightweight student model? Simply fine-tuning the whole model at once can be unstable, especially noisy label data. That's why we develop cycle training. It's a three-step process. In step one, we freeze the main body of the student model and train only the final classification head. This allows the model to quickly learn the specific of the dataset without disrupting the powerful feature it's already had from its pre-training. And instead to we unfree everything and fine-tune the entire model on our new dataset. This is where the model is allowed to explore the learn deeper and more feature from both original and pseudo label data. Finally, we freeze the backbone again for the one last round. Um, this is a regularization step, reinforcing that what the model had learned and preventing it from overfitting or forgetting key information. This process ensures the robust and stable knowledge transfer. And to make our model truly robust against variation in the real world, we also employ a data augmentation pipeline. Our approach is probabilistic. For every image, we first apply a random crop to ensure spatial diversity. Then we make a random choice with 30% chance we apply augment. This randomly select to transformation like changing the brightness, contrast, or rotation. And for the remaining 40%, we use the image as is. This strategy introduces meaningful variety into our training data, forcing the model to learn more general features and which improve the final performance. And so to validate our camera send detection dataset, it consists of about 11,000 images across 30 different scenes, and it's fairly well balanced. Our teacher model is RedNet, and our lightweight student model was MobileNet. And we evaluate the model aspects. First, prediction accuracy measured by top 1 and top 3 score, and the second, runtime efficient measured in the inference latency in millisecond on an astro mobile device. So how did our method perform? This table compares our model against the other top performing method. It shows that our method achieved high accuracy and fast inference speed on the CAM SSD dataset. And to understand where this gain came from, we do an ablation study to isolate the impact of each of our components. This demonstrates that when we combine each component, they all help increase the performance of the model. Here you can see a screenshot of our model running on real in official AI benchmark application. In conclusion, we present a novel framework that successfully bridges the critical gap between accuracy and efficiency for mobile deep learning. By we demonstrate a highly effective method for transferring knowledge from a large teacher to a lightweight student. And our approach achieves high accuracy and fast inference speed on the CAM SSD benchmark. Attention. I'm not good at English, so if you can have any question, you can type it in the chat and I will reply it. Thank you so much.
Thank you for the presentation. So if there are any questions, you can type them in the chat. Looks like we don't have any questions. So we'll move to the next talk, to RepFC, Universal Structural Reparameterization Block for High Performance. And I see already the presenter. Yep, we can see the slides, but we cannot yet hear you. Yeah, you're muted. Okay, cool. Now, can you hear me?
Yes, we can hear you now.
Cool. One more second. Can you see my screen well? Because there's something blocking some content on the slide.
Yes, yes. I think that what's blocking is these tabs from Zoom, most likely.
That's the ones. I'm not sure how to get rid of it.
Maybe you can close them or just, minimize them.
Can I grab it? Huh?
Or just, close. Oh, yeah, it became smaller. One panel became smaller. And the second panel is almost gone.
You're welcome.
Yeah. Good.
Yeah, sorry about that.
No, no problem.
Clear now, and you can hear me well.
Yes.
Okay, good. Hi, everybody. I'm super happy to be here to present our work, RepFC, Universal Structural Reparameterization Block for High-Performance Lightweight Deep Neural Networks. Before I begin, I would take a moment to thank all my teammates listed on the slide for their valuable support, contributions, and all the nice discussions. Moving forward, we have structured the presentation as follows. I start off with the introduction, then talk about the state of the art in this field, what are the core contributions in this work, and some experiments, how we validated this, and then a final discussion section. So let's begin with why we're interested in structural reparameterization. The motivation is quite straightforward. We are interested in mobile or edge use cases where resources are constrained. And here we want or we demand super high performance at the lowest possible latency. And how is it done? By convention. If we want to improve performance, we normally increase the complexity. And by increasing complexity, I mean we go for deeper layers, wider networks, branches, residual connections, new operations, and so on. So what does this usually result in? So we want high performance, so we boost the complexity, and that results in a very high latency. So that is a problem, and this is what we want to address. For this, we look into structural reparameterization methods that address this problem with a bipartite or a dual network design. What do? We push the high network complexity only to the training phase, and then collapse the network back to have a low latency inference variant. What do I mean by this? As you can see on the right, we have a simple network. We start off with a simple network, and what we do is we use structural reparameterizable blocks to expand some of the operations. So state of the art has done for conv layers. So we expand the blocks or one conv layer into multi-branch SRP blocks and use this during training. And just before deployment, once we're done training, we collapse this into the original model so that the deployment is lightweight and efficient. Yeah, this is clearly shown. So there's back and forth. During training, you go to SRP conv, and for deployment, you come back to the original conv. And this already exists for conv layers. State-of-the-art universal blocks exist, meaning you can plug one of these blocks that you can see on the slide. The first block is called DBB, Drivers Branch Block. So there are 5 branches, as you can see, with varying operations, and the yellow bars are the batch norm layers. So you put this block into all the conv layers, train it, and when you have to deploy it, you collapse it back into a single K by K layer, as this is seen here. K by K is a kernel. And another variant is OREPA, which also addresses the same problem. And what it does is it moves the batch norm outside of the block and says you can speed up the training by also fusing it online. So it's also online reparameterizable block. And we put more state-of-the-art models here. So there are a bunch of models called RepBGG, RepVIT, RepNext. So they all use reparameterization for handcrafting their model architectures. So they're architecture dependent. And there are a bunch of models, DBB or OREPA. These are not models per se, they are blocks that you can plug into any state-of-the-art DNN that has convolution layers.
and utilize the technique of structural reparameterization. So the DBB and OREPA are universal plug-and-play blocks, but RepBGG, RepVIT, RepNext are singular architectures that have exploited or leveraged structural reparameterization. And there's RepNAS also trying to lower the training time overhead, because since we're expanding each conv into a multi-branch block during training, it obviously comes with an overhead in training time. So there is one paper that has attempted to lower this overhead by searching for these blocks and different branches in different conv layers. So as you can see, there are some crosses, and most of them do not support blocks for reparameterizing the FC layer that is also commonly found, and these days also employed throughout the network, not just in the head as it used to be. And with our work, we say here you get a universal structural reparameterizable block for the FC layer, addressing the research gap that exists. So the core contributions are as follows. Like I just said, there is this universal SRP block that you can use to expand FC layers. And what we also do is we have multiple variants of this RepFC block in terms of different number of branches, having a batch norm post-processing or linear scaling like in OREPA. So these are the different variants that we use for different architectures. And then we also show experiments on ImageNet where we boosted accuracy of the state-of-the-art by 1.46 percentage points when you train from scratch using these blocks, or you start off with a model and fine-tune them with these blocks. So both are supported in our work. The methodology is as follows. So other state-of-the-art blocks for conv, they expand the conv layers. And here we have designed a block for the FC layers. So we expand the fully connected layer with our RepFC block that looks like this, as follows. So this one is RepFC3, meaning there are 3 branches. And what we do is we send the feature vector, and that's masked in using different patterns. And so that goes on to different branches and then processed. Post this, there's a batch norm layer or a linear scaling layer, and then you add everything up. So the change in RepFC5 is, again, the number of branches and the mask patterns. As you can notice, the mask patterns are usually complementary. So when you fuse it into a single FC layer at the end after training, so after training, there's usually a batch norm fusing, and then you collapse everything together into one FC layer. And because we have these complementary masking patterns, it's straightforward to collapse it after training. Evaluation on ImageNet 1K, as you can see, we have standard trained from scratch using RepFC blocks on a bunch of models. We have used the models that are also in other SRP papers, for example. And AlexNet here has 3 FC layers, so we start off with that, although it's an old one. And here you see that there are more FC layers and more improvement after you put the FC block in these layers. So here, if you can see the difference in the percentage of accuracy between the baseline performance and the one boosted with RepFC5. There's an improvement of a maximum of 1.46 percentage points. And this is the same for also newer models, including MobileNet V3 large. Then we also plug it into some transformer models because now there are more and more FC layers. Although there's moderate or modest improvements in Swin Tiny, where there are even more FC layers, we plugged it in all the MLP blocks. There is significant improvement also with a fast VIT model. And then we try to compare it with the state-of-the-art SRP blocks, where DBB is the one that expands the convolutions. So this paper basically expands all the conv layers as opposed to our work that expands only the 3 FC layers. So of course, the training overhead of their work is much, much higher than ours. And we still manage to outperform them with a higher percentage point improvement. And another important point to note is our work is definitely orthogonal to other works because we only touched the FC layers, while you can still use the other state-of-the-art SRP blocks for the conv layers. So if you have the budget for training time overhead, you could put the other universal SRP blocks for conv in the conv layers and rep FC in the FC layers. Not only you can train from scratch using our rep FC block, you can also fine-tune a model once it's trained, and during the fine-tuning stage, expand it with the rep FC block in all the FC layers, and still gain performance improvements, as it's showcased in this table. Finally, the notable takeaways are we have delivered a block that you can plug into any state-of-the-art model for training or fine-tuning and boost your performance. There is no overhead in inference time because we collapse it back to the original model post-training. And because we do not expand on all the layers, we have a significant benefit in terms of the training time accuracy improvement trade-off. And like I said, we are capable of just boosting performance orthogonally, not hurting other works for conv. Thank you very much. I'm Shambhavi from Technical University of Munich and BMW Group.
Thank you for the presentation. So do you have any questions?
Yeah. Okay.
Yeah.
So how does the inference time compare to the other SOTA method?
The thing is, inference time is the same as the original model, right? So you start off with a model, you only expand it during training to boost performance, but the latency is the same as the original model you started off with because you come back to the same layer. Yeah, thanks. Yeah.
You mentioned that you only replace some of the conv layers with, the tech layer with RepFC in order to, optimize this training time to a performance ratio. How do you choose how many conv layers to do and next time doing them yourself?
No, I got your question. Yeah, I got your question. With that statement, what I meant was in classification models, for example, the dominant operation is convolution. And with the other SRP blocks that are expanding convs, they expand the entirety of the convs, whereas in the same model, we only expand one FC layer in the head and still outperform them. That's what I meant to say. Yeah. Yeah. Oh yeah, this is also a good question. We did not compare it with mobile one, but again, it is not a universal block. It is architecture dependent. And I think they did it for conv layers. This is addressing the FC layers. Yeah. If there are no questions, thank you for your attention and have a nice rest of the evening.
Yeah. Thank you for the presentation. Yeah, so we had the last speaker today, and now we are moving to the end of the workshop. So we have now time for discussion. So if you want to ask some public questions, we can discuss them right now, and you can also ask now the questions about the competitions if you have ones. Yeah. Is there anyone on Zoom who has questions? Or anyone in place at CVPR who has public questions? Okay, so if there are no questions, then I'm stopping now the recordings, and we can say bye to all future guys who would be rewatching the recordings. So again, we were streaming this workshop on YouTube, And you'll be able to find the recordings of all talks, all presentations, just using the same link as is published now on the workshop webpage. So everything will be recorded. You can rewatch everything when you want. If you want to check something again, just feel free to do this. And yeah, therefore, we end public part right now. And yeah, so I say bye to everyone who watched us on YouTube. Okay, and